All righty. Let's see. A few more minutes before we start. Hey, Jonathan. Yeah, that's a good question. Complete all 9 passages today for phase one, or is that a typo? So, are you referring, Jonathan, to phase one for PsychSoc? Is that? Yeah. Okay. Cool. Um, yeah. So when it comes to the PsychSoc books, it's kind of interesting because they're formatted in a different way. I mean, each one of these kinds of books have different authors, and um, I think the phase one, two, three kind of methodology works best for chem phase and biochem. This one's a little tricky because there's less questions. So yeah, exactly, Jonathan. So there's the style is a little different in that they try to focus more on getting you comfortable with the material. And then from my experience of looking at this, then they hit you with a few but really hard passages um, that, in my opinion, are more like the ones that you would want to take slowly. So not necessarily like cram them all in 1 second, in one go. And like with the other sections, these passages have yeah, definitely into 2 parts. I recommend dividing into 2 parts because, like the other books, these passages have questions from other chapters that you haven't covered yet, which is an intentional thing. They try to get you, even though you haven't seen the information, it's this um, idea of like learning through the mistake and reading the reasoning. But with particularly with the psych I find that if you don't break them up, you're just going to make a lot of mistakes at the beginning. So my recommendation would be to perhaps look at like half of the single questions and half of the passages. And I was going to propose to you all, if you all wanted, if we had time at the end of the lecture, to look at passage number one together, if you guys think that would be cool. But yeah, one vote from Jonathan. Okay. Well, we have, uh, yeah. Oh my God, my thought process. We don't want to go there, but yes, but for sure. So I've heard there's like about 50 of you, and I see there's 26 of us, so that makes like I would say critical mass. So let's get started. Yeah, for sure. Definitely there's a thought process that goes into the psychosocial part because as we'll find out together, the material isn't too hard. It's pretty straightforward, but it definitely there can be it seems like a disparity between how easy the material is, but then how the questions are framed. Yeah, Sophie, thank you for bringing that up. I do you did you get it in an email? Can some people tell me if you got an email from me about 30 minutes ago? Okay, cool. Awesome. I can Okay, cool. You see it now? Okay, great. Awesome. You did not. Oh my goodness, Jonathan. Okay, how do I attach that? Does anybody you didn't either? Okay, so it sounds like we need to attach this. How do I do that? From my computer? Sensation. Oh, thank you, Stephanie, as I'm struggling here to figure it out. Okay, so Stephanie sent it in the chat box. Thank you so much, Stephanie. And yeah, Jonathan, maybe let's chat afterwards so that I can get your right email because I sent this to the people that I had in the email list. So maybe they have your email wrong. And a few of you also if you didn't get it. Okay. Why so much reading today? The lecture slides are long. Yeah, yeah. Welcome to Psych Social. Okay, but let's get started because as Sophie pointed out, we have quite a bit to do. So let me share my screen. And hopefully you see the slides. Can anybody confirm that you see slides? Yes, great. Okay, cool. Awesome. All right, I'm gonna take off my camera because I've heard that helps with the video. I don't know if it's fake news, but I'm gonna stop the video. Okay. And so Manri, yeah, you have access to the slides in the email that I sent. Would somebody mind, maybe, I realize that when people show up at different times, they aren't able to um, see if it was posted. May somebody post one more time the slides? That would be so great. Oh, there's a Discord. Okay, thank you, Stephanie. Y'all are way more fancy than I am. Okay, let me get a start on this. So, okay, there's a request for me to keep the video on, and then if it gets laggy, okay. All right, perfect. All right, so welcome everybody to Sensation and Perception. It's, I believe, your first psych social lecture that you have, and I'm very excited to be joining you all for 4 of these lectures, which will pretty much cover the content for the psychology portion of the psych social. I'm Diego, and I'm a pre-med like you. Took the MCAT in the summer, so in June, and I took the Berkeley Review course just like you did, the online version, back in the spring. I studied literature and creative writing and French at a very small liberal arts college in Switzerland called Franklin College, Switzerland. And you would think that that would have made me a pro at cars, but alas, it did not. I only scored average in cars. But I did get a 97th percentile in psych social, so I think that explains perhaps why I'm here today. So let us, but before we get started, I wanted to get you a little bit of an overview of psych social. It is a section not unlike the other sections except for cars in that it has 59 questions that you have to do in 95 minutes. And I've indicated here some of the things that they tell you that you need to know. And these come from the AAMC, so that you can kind of check out that part. What I find more interesting is perhaps that they have divided you what the psychology sections is, the content, the sociology, and the biology. And if you want more information, you can check out those links also. So one of the things that I did want to do, though, was to take some time to dispel the myth that this is just going to be a content-heavy, term-heavy section, and that all you got to do is Anki your way through it. And I don't think that's quite the case. I think that if you get into this idea that it's just going to be a bunch of terms, you're going to sadly realize that once you're looking at the passages and the questions, that the terms alone and their definitions won't get you anywhere. But it is, however, important that we do look at the terms and that you understand them, I think, in their logic more than in their definition. Psych social can be also a really great way to end the exam because it's one of those that I find that you end up recognizing more of the terms than you actually need to you end up recognizing the terms more than you need to define them. And so that makes it a little bit easier, in my opinion, sometimes if you really have a clear idea of what those terms are, that you actually reduce the amount of memorization you have to make. But what I've tried to do along the way is italicized some of the terms in these lecture slides that I think will be essential for you to be familiar with. And in some of the cases, I've put the definitions, and in some of the cases, I haven't put the definitions on them, because that way, hopefully, you aren't right now with your camera off in your bed. I know it's early Sunday, but instead you're on a little desk writing or doing something like that, so that you can kind of stay active with this a little bit. So, and more than me making you stay active, it's the idea that you want to end up putting definitions in your own words, always, for this section and all sections. Alrighty, so let's move on. Okay, so, oh my goodness, do I have these little annotations lingering on the, my God. Okay, this is the last attempt of me getting fancy. Sorry, folks. Okay. All right. So, oh, one last one. I'm sorry. My anal retentive brain won't be able to focus until I get that little one. All right. And to Cameron, I sent an email with the slides. And hopefully you can see the slides right there in your email that I sent half an hour ago. So these are some of the contents that we're going to talk about today. So this is the overview of the whole presentation. So I highlighted 3 areas, and don't hate me in saying this, but we're not going to go over these 3 areas today. There was a decision I had to make, which was that either we cover all of these areas and that you get not everything of the content, or that I would give you everything of the content you need to know for these other ones. And then in what I'm propose we do is, in over office hours, spend a few minutes looking at these other 3 areas, if that's okay with you. I think personally that's a little bit better, because the AAMC will show later how they really use heavily the ones that we're going to talk today. And the 3 that aren't highlighted are perhaps a little less used. Okay, enough of me talking. And I have a question for you all. So I know that we have some people in the room who are psych majors and whatnot. But whether you're a psych major or not, I want you to answer this question for me, or I guess these questions. What is sensation, in your words, perception, and how are they different? All right. Time to type in the chat box. Okay. Mm-hmm. Uh-huh. Yeah. All right. Oh my gosh. Oh my gosh. Everybody knows basically what it is. I think you're ready to take the MCAT now. No, but everything that you're saying is right. And those that have been writing things, and I'm sure that if you weren't writing, you were probably thinking the same thing as most of these comments, which is the fact that sensation is right. Like Sophie just last said, it's very much about the stimulus. It's about the receptor, and perception is a process of interpretation. Another way to think about this too is that that sensation is a very passive process. Sensation is occurring all the time because of physiological processes that are accepting stimuli, whereas interpretation is a very active process. And it has to do a lot more with the organization, selection of all the sensory input that we get in, which is quite complex. And so that's why it's kind of nice to think about it as a passive versus active process. Alrighty. So the first thing that we're going to talk about is precisely on the side of the sort of passive process, which is going to be the psychophysics of things. I think that if I'm not mistaken, if the calendar that I read is correct, you just finished a neuro lecture. Is that right? Yes. Okay. You poor souls. But if you just finished a neuro lecture, I'm glad to say that I'm going to skip over the two that I've just highlighted over here, which is the type of sensory receptors and the sensory pathways. If you guys are game for me to do mini lectures in office hours for somatosensation and the other things we missed, I will talk about these other two highlighted things then. Right now, I'm not going to talk about them because they're a little bit more specific on the neuro side than they are on the psychosocial side. And there's already a bunch of pre-med saying, yes, I want to learn more. Okay, all righty. But let's talk about the first one here, which is the thresholds. So we're going to skip over the part where we know what a neuron is and we know what action potentials are and how they processes of excitation and inhibition. And now we're just going to talk about the thresholds. So thresholds is the idea that we're going to find a limit of sensation. So remember, we're focusing on the sensation part, which is the passive process. And a threshold itself, or also called the limina, is going to be the amount of stimulus that's required to render a difference in sensation. So basically, as this diagram is showing over here, there is you go from 0, meaning there is no sensation, to 100, meaning that there is suddenly sensation. One way to put it in an example is like if you're trying to, let's say, what is the lowest decibel of loudness that you can hear? And so there's going to be a number of decibels until you reach a point where you start hearing. And so that's going to be your threshold. It's also called absolute threshold because in the sense that absolute is that it's binary. It happens or it doesn't happen. And so when it comes to absolutes, we talk about it as an on or off kind of thing. You feel it or you don't feel it. If you feel it, it's what is called the threshold or the limina. And if you don't feel it, or I should say sense it more accurately, then it's called subliminal. Kind of makes sense, liminal, subliminal. And then because reality is such that everybody's faculties of sensations are different, we have actually more of the red curve that we see in this graph. And the red curve is one that takes into account that not everybody will sense equally at the same thresholds, and also that different circumstances change how individuals would be able to hear that. For example, with the sound example of like trying to hear the lowest decibel possible, if you're doing it in a quiet study room, it would be different than if you're trying to do that same task outside in the city, for example. So because of that, we use different thresholds. So the difference thresholds is, yeah, let me clarify that. Morale, hopefully I'm getting that name right in pronunciation. The blue lines represent an ideal absolute threshold, meaning that you go from 0, meaning that there is no sensation, to 100, that there is sensation. Absolutes is something that we think about theoretically, but in reality, we're going to look more at the red line, which is that gradually you go from no sensation to 100 or a sensation. And then there's a point there in the middle. It freakishly looks like oxygen saturation curves. It gives me like PTSD. But the point in the middle is going to be right. Yeah, Melody, that's correct. So so as you increase gradually, receptors are being stimulated, but whether or not it's like an increase in receptors being stimulated, what makes it register as a change is once you get to 100 and the brain has made the interpretation of that sensation. So don't focus too much on what the receptors are doing on the way from 0 to 100. Just realize that somewhere along that path is where you're going to, let me say that better. That instead of going from 0 to 100 in the blue way, we go from 0 to 100 in the red path. And so because everybody has differences in what 0 and 100 means, we use difference thresholds, which is defined as the stimulus intensity detected 50% of the time. And this is way more important for us than absolute thresholds, because we couldn't have a textbook say like the absolute threshold for hearing is X decibels, because then we would have way too many values, because it would depend on context and it would depend on people's hearing capacities. Instead, we use different thresholds. And so they say 50% of the time it's detected. That way, it takes into account the fact that it could be a little bit over or a little bit less. Another part to talk about is the just noticeable difference. And in the example that I was saying, we were talking about a difference of sensation from no sensation to suddenly sensing. The just notable difference is slightly similar, but in that we're talking about, let's say we already are hearing, but we want to hear what is the next point that we're going to hear a little bit louder still. And so that is the difference, just noticeable difference. So basically, as you're kind of going like, okay, each little step increment. I like to think about the just notable difference instead of sound. I like the weight example, which is that you're lifting a 2-pound weight and you go to a 4-pound weight, and that's the next time you detect a difference. Right, exactly. Exactly, Sophie. Yes. So what Sophie just wrote in the chat box is exactly what the just noticeable difference is, or rather the way that I like to think about it, which is that that as we're smaller in the in the differences, like you start with 2 pounds, you double that, and that's when you first experience the doubling. But when you're at a very high number, like 200 pounds, adding 2 extra pounds, you won't feel the difference. So to then have a difference that is noticeable, you must increase by a factor of like maybe 300 pounds at that point. Yes, thank you. Aditya, thank you. Yeah, that's exactly a good way to synthesize it. The absolute threshold is definitely not calculated. Rather, it's some concept that we think about. Yes, exactly, 100% of the time, right? And the thing that we do calculate is the difference thresholds, because those are 50% of the time. The last thing I want to say about this slide is that there's the Weber's law, and that's something that you have to know for the psycho section. It's probably, I would venture to say, the only formula you need to, maybe it's the only formula you need to know for this entire section. And it's a pretty straightforward one. It's saying that there's a constant, which is K, that equals to a difference in intensity over the original intensity. I like to think about this in terms of the difference of intensity being like we were talking about the pounds. So let's say that something has a Weber's constant of 0.5. I like to think about that in terms of 5/10, right? That makes is that right? Yeah. And so I like to think about that in terms of like a very simple fraction. So I'm going to try to annotate one more time. So my theoretical K is 0.5, which in turn, I like to think about it in my little brain to make my life easier as 5/10. So let's say the original intensity we're going to call 10 pounds. And for example, the difference is 5 pounds. Then we could also say the same thing of, let's say we increase this to, you make the fraction a little bit bigger. So the value is the same for the constant, but now we're saying that if we have a 20-pound weight, then the change in the intensity would be 10 pounds. So to go back to what Sophie was saying was that if this is my K constant, then I say, okay, I have a 10-pound weight. How much heavier does the weight have to be for me to notice the difference? it has to be 15 pounds. Why? Because this value is at delta I, which means that it's 15 minus 10. Does that make sense? I know this is a little bizarre to think about, but give me some feedback. Backwards math, yes. Okay, it makes sense to Jonathan. More thumbs up? Actually, don't give me a thumbs up because I don't know if I can see them, but tell me in the chat box. Perfect. And just to quickly go over this example. So what I'm saying here is that if you have a 20-pound weight, now you all tell me what should the next weight be so that yes, I'm seeing 30s. Everybody say 30. Because why 30? Tell me why. Tell me why. Yeah, just noticeable difference. Right, yeah. Would it be add minus 10 to feel the difference? Yes. Yes, Tiffany, what you said is correct. Okay, good. Alrighty, I'm getting a sense that people understood this. This one is can be tricky because they can give you like a scary number of like 0. I won't write it out because it'll take me too long, but they can give you a scary number like k equals 0.037. No, I sent that directly to memory. K equals 0.037. Okay. So that's kind of when I see that, I'm like, like, no, this is going to be crazy. But now I'm thinking backwards math. I'm thinking, okay, I'm going to make my life easy, and I'm going to say 37 over 100, which means that the original intensity is 100, which means that in order for me to feel the next one, it's got to be 137. So hopefully that makes sense. If it doesn't, we'll talk about it later on after the lecture. All right. So let's talk about signal detection. So far, we've talked about the stimulus, whether it's sensed or it's not sensed, or it's sensed 50% of the time, which is the difference threshold. But now we're going to talk about the decisions that also go into play when we're experiencing a stimulus. So there's a decision-making process that we have to do that's called the signal detection theory. Normally, it's presented with this red figure that's on the far right of the slide. And I kind of don't like that figure at first because I kind of don't understand what it's saying. Instead, I like to first focus on the one in the center of the slide. So what this particular theory for decision-making is telling us is that we have 3 elements going at play. One, which is in the top of the box, which has the stimulus is about the stimulus. The one in the left-hand side of the box has the subject's response, which is saying like whether we sense the stimulus or not. And then a third one, which isn't present in this box, but is present in the red one, is a concept of noise. So instead of, let me tell you an example, because I think examples help a little bit more. So say you are, you're driving. I live in the Bay Area, so quite often when you're driving in the mornings, there's fog, and if you're me, you're always running late, and so you hit, you're driving down the road and you see a stoplight, and you kind of think it's an orange light, but you kind of think it's a red light. And Bay Area driving, you're like, if it's orange, I'm going to take it. Well, even LA, like probably even worse for some of you in LA. So the idea here with signal detection theory is that I sense there's light. However, I can't detect whether it's red light or orange light precisely because there's a noise, and that noise is going to be fog. So my decision that I have to make is whether it's there or it's not there. So that's what this box on the left-hand side says. I'm saying whether the orange light is present, um, or I keep on saying orange, I should say the yellow light is present or it's absent. So let's say I say it was present and it actually, and yeah, so if I say it's a yellow light, I'm going to take it and go through the intersection and it was present, we call that a hit. If I say the yellow light isn't there, it's actually red, I'm going to stop. And if I was right, if it wasn't a yellow light, we call it a correct rejection. Then comes the issues. I say the yellow light is there, but in reality, it wasn't. It was a red, and I crossed it. So that's called a false alarm. Uh, and then the alternative is that I say, no, that might be very much a red light, so I'm going to stop. But it actually was a yellow, and I could have taken it. So it's called a miss. By the way, I'm not encouraging you. The yellow is meant for you to slow down and stop. It's not meant for you to like hustle and get through. But anyways, that's an example. So hopefully that example clarifies how this box works. Now we can look over at the red one and then realize, okay, so what these are saying is that we have correct rejections, which is the light red little mound, and hits, which is the black mound. Where there's an overlap, and you can see kind of how they're reversed on either side of the criterion line, is where those mistakes happen. So our interpretation of the stimulus is actually incorrect of what reality has. And those parts are due to noise. So this is signal detection theory, and it's something that definitely will come up in the MCAT. And one of the ways that it'll come up in the MCAT, I think, is in really interesting examples that aren't stoplights, but instead are things like a radiologist is looking at a CT scan, trying to determine whether a blotch in the CT scan is an error of photography or if it's a tumor. So that's kind of a medical reasoning, right? I like to think about that example because the real world examples help me understand the concept, but I kind of want to get it as close as I can to medical terms. So in those examples, it's really important for the person to realize that the psychology behind it, that there is a stimulus, but then there's a decision about the stimulus that we have to make of whether it's present really or it isn't. Yeah, so so for the concept of noise, Sophie, it's I think to think about it more in the sense that noise means that in the real world examples, whether it's like out in the street with fog or in CT scans that are not going to be absolutely perfect for detecting things every single time, that there's just like random error that can take place. And so that could be the thing that's noise. Or also in terms of, instead of error, maybe think about it as like there's a stimulus and then there's your reception of that stimulus, and there's always going to be something in between, right? So the idea is that noise is ever present, and so that affects our ability to say like if the stimulus is there or not. Okay, so that's all I want to say about that. All right. So now let's talk a little bit more about the adaptation to things. This is pretty straightforward, and but it's a pretty interesting one that I like to think about in terms of like right now you've probably forgotten that you were sitting on a chair. If you are sitting on a chair, you might be in your bed because it's early Sunday morning. But if you're sitting on a chair, you probably sat down sometime around. Now you're thinking about it. Yes, yes, and we'll talk about how that happens. But before I mentioned it, you probably had forgotten you were sitting on it. So the question I have for you is, did that mean that the neurons stopped firing? Did the neurons in your butt stop firing and sending signals to your brain? No. Okay. Yeah. Yeah. We just tune it out. Exactly. So, so the idea is that sensory adaptation exists, and like the adaptation word, does it ring a bell in terms of evolution? And I hope it does, because that's the idea behind this concept, is that evolutionarily, one of the developments that our senses have allowed us to tune out certain things, which is a good thing. Because can you imagine the fact that if we had to be present every time we took a breath, or think about our butts on a chair during the entirety of this lecture? So it's a good thing for us to experience this decline in the sensitivity to a sensation. And there's two main ways that that happens. And they're in this diagram. One is a slow adapting receptor, and one is via rapidly adapting receptors. So this basically means that there's two big categories of receptors, cells, neuronal cells, that are responsible for sensing things. And then how do they adapt over time? The first one is going to be, as you can see, in both of these examples, the stimulus is on. So if we're using the chair example, the stimulus is on as long as you're sitting. So like you all said, the neurons didn't stop firing. They're still firing constantly with the same, at the same frequency, with the same millivolts. The difference here is that the receptor is going to kind of phase out how much signals they're sending to the brain. The first one also has a name of tonic. I recommend you write that down because that's going to come up. So A is also known as tonic. B is known as phasic. And B is distinguished because it has, like the first one, you sense it pretty quickly, but it phases out pretty fast. Phasic. B is phasic, like phase, but ick at the end. And so it helps us kind of tune out certain things. And so you can see the importance in both of these categories and that they light up. That's correct, Stephanie. Thank you. You can see that these both light up instantaneously for when the stimulus starts. And that's a good thing because that way we want to be attention to the thing. But we also don't want to be on high alert all the time for absolutely everything happening, which is why they go down. Let's see, what else do I want to say about this? Oh, a really important thing, probably one of the most important things about this lecture, because I'm going to tell you this, and you're going to make this mistake anyways. Don't confuse this with habituation. Listen to me. Don't confuse it. You're going to confuse it anyways, because it's just going to happen. But sensory adaptation, because you won't come across the term as sensory adaptation. It'll just say adaptation, and you're going to think it's habituation, which it's not. And the problem is that it's very similar. The concept of habituation is similar to adaptation, but we'll talk about habituation when it comes to learning. Then I think more about Pavlov and his little doggy. That's habituation we'll talk about later, which is a central core process that is way more about psychology than it is about neurobiology. Okay. And that's about it. All right, I'm going to move on. And that was the end of psychophysics. Yay. Okay, so any questions about signal detection theory, thresholds, sensory adaptation? Yeah, so Sophie, the tonic provides continuous decreasing signal. So that's the thing in both of these. They're both decreasing. It's constant. Both of these have the same stimulus strength, which is illustrated in the red on the bottom of both, and they both decrease. But the difference is that tonic decreases slowly, whereas phasic goes down to baseline almost instantly. And adaptation and habituation. Yeah, so adaptation, Melody. Yeah, you're doing the right thing, Melody, but trying to get it straight now at the beginning. Adaptation has to do with the neurons. Habituation has to do with the learning process that we haven't talked about yet, but we will talk about later, which is the fact that when the bell is rung that is coordinated with exposing a steak, then after a while of doing that, you remove the steak and the bell rings and the dog still salivates. That's the habituation part, which is a learning thing. Uh, Neurons are certainly involved in habituation, but in a far more complex manner than what we're talking about adaptation. Can I give you an example of phasic and tonic? No. That's a good question. I'll write it down. It's good to have examples in the back of your mind, but to be perfectly honest, I can't. Yeah, pain, Tiffany, you're right, but pain can be a couple of different things. And we can talk about that in the little mini lectures in somatosensation. Pain can be phasic and tonic. You can have dull pain that lasts a while. Um, yeah, yeah, I like the close more than the pain because pain you can get into ambiguity. But uh, I'll get back to y'all with examples that are nice ones. Okay, all right, let's move on. We're gonna move on to the first of the sensory systems. This is perhaps the most tested one of them, what we're gonna talk about. We're gonna talk about vision, and we're going to divide it first by the sense, and then we're gonna talk about the perception of it. And all of the senses are really complex, beyond the scope of the MCAT. But I think the reason why they like to talk about vision so much is because pathways are pretty clear and it's kind of elegant how it works and it's very easy to explain. I think when it comes to the other senses, the ones that I highlighted for later lectures, those are actually very much under research. I mean, the vision still is too, but the other ones are still in like discovery phase of how a lot of these things work. And so I think they like to rely on this one a lot. So pay close attention to everything we go through in these next sections. All right. So we're going to talk about the first thing, which is light. So I know you haven't gone through the optics section, but you might be already savvy pre-meds and you can let me know a little bit about light. So light is going to be the stimulus that begins the visual process. Light is electromagnetic waves. And how do they travel, by the way? Let me give you more context. Do they travel as longitudinal waves or transverse waves? Oof. Yeah, yeah. Uh, these are all good guesses, and they're all wrong. Thank you, Iman. And it's transverse. They're transverse waves. And the waves consist of, and you'll go through this in physics, so don't even worry your little hats off. Yes, that's right. So they are longitudinal waves, and so basically, I won't go into detail as to like what distinguishes one and the other, but basically know that light is transverse, meaning that the direction of the movement of the photons is transverse of the orientation of its displacement. God, I made that even more complicated than it should be. Anyways, I'll let Todd talk about transverse, and they consist of wavelengths, amplitude, and purity. So the thing that you just need to know for psychology is what these things, so these are the physical properties of a wave that are in the bullet points, but they translate to sensation and perception later on in psychological terms. So what does wavelength translate to as in psychology? And if you don't know what I'm talking about, look at the little brown box in the upper right-hand corner. Yeah, hue or color. Amplitude is going to be brightness, and purity is going to be the saturation of the color. And saturation is one that you might not be familiar with, but it's just basically the fact that you think that a color is really a very dense color. So you would think of a saturated red as like, I don't know, the color of a rose, and pink would not be a very saturated red because there's a lot more white that went into it. Um, so you don't need to know about hue is going to be just the color. Like it could be pink, it could be red, it could be like light red, it could be pink. Um, it doesn't matter. It's purity has to do with the fact that you add white. So imagine hue as the fact that you go to Home Depot and you buy a bucket of paint. And so you buy the hue of yeah, the intensity. That's another way to say it. Yeah. And you just add it. So you have a bucket of paint, and that's going to be the hue of it. But when you start adding white paint to it, then you're diminishing the saturation of it. That's all you need to know about saturation. And so this picture over here is not something you need to know for psych-social, but it's a nice picture to remind you of what white light comes in, which is light at various different frequencies. It goes into a prism, and then through a process of refraction comes out on the other side of the prism, divided into the spectrum of white light, which in terms of what we see, it doesn't mean that there isn't light underneath or above the spectrum, but what we see is somewhere underneath like 350 nanometers to 750 nanometers, thereabout. At the bottom of the diagram, you see that light actually can come in a variety of frequencies and wavelengths, and those are seen from gamma to then the stuff in radio. But what we see is the little rainbow things over there. Okay. So that's light. But then we have an instrument to see the light, and it's a pretty beautiful instrument. I can see very easily why people want to go into ophthalmology, because it's a really elegant instrument. So, but it's a pretty simple function, which is that you try to get the light to go from outside to the retina. And then the other main function of it is that you want to keep the retina in there. You want to keep it safe, and you want to keep it healthy and happy. So this diagram, I want to say it might be a little too much to know, but at the same time, I think it's exactly what you need to know. I would venture to say that you need to know almost everything on this diagram, except for things like nodal point and limbus. But it wouldn't be a bad idea to like take this, white out the things, and then write the things back in there. And but don't fret too much about it. This is not going to be an anatomy test, but it is one that helps if you're thrown anatomy terms and you're already familiar with them. So that's kind of the way to think about anatomy in terms of the whole of the MCAT, in fact. So light travels, and it goes in through it. Right. Right, exactly. Thank you, Amanda. Memorize it, but don't memorize it. I know, I love it. So your light goes through the cornea, and then it goes into the anterior chamber, which is filled with fluid. And then it goes through an opening that's called the pupil, that's surrounded by the iris, which is the colorful part, the ring that's like a bunch of muscle. It's a bunch of muscle. Why? Why is the iris muscle? Why is it musculoskeletal cells? Anybody have cats? Yes, contraction and dilation, exactly. Yeah, perfect. I have an cat next to me, that's right. So that's why it's musculoskeletal cells. And then it goes through the lens. And the lens is an amazing optical instrument that is basically how glasses that we wear work. Because of properties of the lens, and because of Snell's law that tells us about the bending of light that comes in through it is bent in such a particular way that once it exits the lens, it hits the retina as close to as possible, center around the fovea, which is all the way down if you follow the dotted line down to the fovea, which is a point we'll talk about in just a second on the retina. The other chamber that you have other than the anterior chamber is the vitreous body, which is the big chamber there, and is also filled with fluid. That's all you really need to know about it. I mean, it can get certainly more complex, but that's all you need to know. The other thing I want to point out about this is that you have the optic nerve, which is that yellow nerve at the bottom of the diagram. And that dense part of nerve right there is doesn't have the retina going over it. So it's what we call the blind spot, because imagine you have the retina covering sort of the majority of the circumference of the eye, except for that spot where the nerves enter and exit from. So it's not very clearly seen here, but just, yeah. Oh my goodness. What did I do? Oh my God, I broke it. So sorry, folks. Okay. Careful tapping. Alrighty. Oh, one more thing I want to say about this, and you should write this down because I didn't write it on the slide intentionally, but I have it in my notes to tell it to you. Accommodation. Write that down because it's a term you're going to know. You need to know. Accommodation is a process in which the curvature of the lens can change. And this is something that our eyeglasses can't do. They don't change, but our lens is really cool and it does change. Accommodation is a thing that allows for the bending of light to change depending on whether we're trying to see objects that are far from us or near from us. And all you need to know for accommodation is that if the object that the eye is trying to focus on is closer to you, it gets rounder. And if the objects are far away from you, generally like 20 feet or 25 feet farther, then it begins to flatten out and get kind of like a pancake. And so that's really important because if you don't have the process of accommodation, then you can imagine the light rays would land in the same spot every single time. And you would either be able to only see near or you would only be able to see far. And the other thing to mention about the iris that I forgot is that it can, like you all said, it constricts and relaxes, and that's to regulate the amount of light that goes into the eye. Okay. The lens flattens out or rounds, whatever it needs to do. And the lens in the diagram is that white thing right on the top. You know, like, can y'all see it? It says, oh, anyways, I don't want to use a little pencil because it's more trouble than it's worth, but the lens where it's indicated right there. Okay. So let's talk about the retina, which is where one of the, like, basically the main function of the eye is to house it. And so light gets to the retina, which is where we start seeing neural tissue. So up until this point, light has been traveling through physical structures, and then it reaches this one, which is going to be the first spot where light energy is going to be transduced into neural impulses. And so there's the retina here in the diagram. The reality, though, is that it's as thick as a credit card, more or less. So when you think about it in microanatomy, that's a pretty thick thing, you know, like the thickness of a credit card in your eye. And the light, can you all tell me where the light first, the path of the light in this diagram? Let me phrase that question a little bit more. Okay, so yeah, from the ganglions to, yeah. Yeah, so Tiffany is proposing that the light travels, or the light energy gets somehow from the ganglia to the rods and cones. It actually turns out to be first to ganglia. Right. So it turns out to be more of like what Zoe's saying, which is the opposite of what's intuitive. But light is traveling and it arrives first from the top of the diagram where it's the blue, the light blue. And it actually is going to go through all of those cellular structures and hit the cones and rod cells, the purple and red cells first. And that's where the process of light changing the stuff that's inside compartments of those cells will begin this process of excitation that then goes back up the diagram and then out through the nerves. I think this one is worth me annotating on so that it makes sense what I'm trying to say. Light travels down this way, that way. It gets these cells excited. And then the excitation is carried all the way up and travels to the brain via the nerves. All right. That part was worth me making very clear. So light goes from there, but then signal goes from, yes. The signals go, yes, the signals go from the rods to the ganglia, correct. And there's a bipolar cells in the middle, which we won't go too much into. All of these nerves head in the same direction. So regardless of where this is happening in the eye, they're all going to go towards the optic disc. And the optic disc is that part where I was talking about where the optic nerve enters and exits the eye. And that's also where we have the blind spot taking place. Okay. So I don't know of any specific diseases that cause the light to skip it, but I can tell you through my MCAT reasoning that it's not possible for, if the rods and cones aren't doing their job, it's not possible for us to perceive the light. Obviously, the stimulus would hit the eye, but we wouldn't be able to perceive it because the rods and cones, as we're going to talk about on this slide, are the important part for us to be able to change the stimulus of light into the sensation of sight. It wouldn't happen otherwise. So we would definitely need to be able to have those. And so here we have the rods and the cones. And as the diagram shows, they're like two little funny brothers. The rod is good for scotopic vision. And scotopic means that it's good for low illumination is the fancy thing, or AKA nighttime vision. And they're good for peripheral vision. The concentration of the rods are outside of the fovea, and the fovea being the spot down here at the bottom of the dotted line, which looks, in this slide to look like the indentation. And then they're concentrated just outside of the fovea and then throughout the retina. The important thing to realize about rods is that they're 100 times more sensitive than cones are to dim light. They're really, really adapted to be able to take in whenever there's low amount of illumination, to be able to do that. They're the ones responsible for us to be able to see around our room in the dark when like all that's coming in is through the window of like night light coming in. Oh my gosh, Aditya, you like stole my thunder. Oh God, I had a good question that had exactly to do with that. All right, but I think I might be able to still ask the question because you didn't say one part to that. But yes, you're right, Aditya. And then they greatly outnumber cones. So I wrote down that there's 5 million receptors in cones, but I didn't write down rods because I want you to write down rods. There's over 100 million rods, whereas there's only 5 million cones. Oh my gosh, that's quite a bit of a difference. But it's exactly what we need in order to be able to do the job of being able to perceive light. Cones, on the other hand, in addition to being smaller in numbers, are more adapted to photopic vision, which has to do with daytime vision, lots of illumination. But that doesn't mean that they're good at saying like, oh yeah, like it's dazzling bright. That's what we're here for. No, they're here for color. And the reason they're good for photopic vision is because without the presence of high illumination, we can't see color. I have a really basic question for you. Yes, I said, yeah, 100 million rods, over 100 million rods. So you can see quite the difference there. So I have a question for you. So when you're in your room and you're there with your brown tabby cat in the room, and she's staring at you like cats do, and you can barely see her, but you see like a dark figure. Did the cat turn from brown tabby to gray black when the lights went off? You think no? Okay, but their eyes kind of glow. They do. They have something in their eyes that we don't, which is a big reflective thing that's good for their nighttime vision, something that we don't have in our optical senses. But no, they didn't change color. They absolutely didn't. They're still brown. The thing is that in order for us to see brown, we need to have light to go to it. Because it's something really basic, but really easy to forget, which is that what we see in the world, everything that we see in the daytime colors, it's actually because light it's not because the cat is illuminated and emanating brown light. It's because light hits the cat and the cat's fur absorbs all of this light energy except for the color brown, and it bounces back off of them. After the excited electrons go down, it releases an energy frequency of the color brown. And so then we see the color brown because precisely there was light. So I want to get that really clear, that that it's not that that cones are good for daylight and vision and color. It's because of the fact that in photopic vision there's light present, and so it bounces off of the cat, and so that's where the cones come into play. And the rods can't pick up color. They can't. They have lots of important things they do, but they can't do the color, and the cones can. And so that's what makes them really important. The rods are really good for peripheral vision, but the cones are really good for visual acuity. And the visual acuity just means basically that the image looks sharp. That what you see is like a very clear instead of like fuzzy details. And then they're concentrated in the center of the retina, and most importantly in the fovea. The fovea is made up only of cones. Like, highlight that. Like, that's gonna be absolutely a test question. They're gonna like somehow throw in there about a fovea and like rods being in the fovea, and your job is to say, nope, that's a lie. There's no rods in the fovea. It's 100% cones. Now, okay, Aditya, I'm going to ask the question that you kind of stole my thunder too, but why do astronomers, when they're looking at stars through telescopes, when they want to look at a star, not look directly at the star, but instead look up or below the star? No guesses? Yeah, yeah, all these answers are right. But to be precise, the reason why we do that is because whenever we want to see something the most clearly, remember cones are good for visual acuity, which is to see something sharply. Like say you want to see your loved one and you want to really see them clearly, you're going to look directly at them such that the image is traveling through your eye and hits the fovea where all the cones are. But the thing is, the cones don't work in scotopic vision because there's not a lot of light. Obviously, the star that's illuminated in there is a little dot. It's not going to illuminate and suddenly become daylight when you look at it. So because you want to look at the star really clearly, it means it's going to direct it right to your fovea. But since it's dark, your foveas aren't active, your cones aren't activated. The only things activated are your rods. Therefore, you have to employ peripheral vision, which means that you have to look right above it or below it. And that way, they'll become illuminated. It's a really fun effect, and I encourage you to do that tonight. It will not be as detailed as detail because to be the most detailed, it has to be in the fovea. So that's the crux of the matter. It cannot be detailed. The only way it can be detailed is by taking a photograph of it, and then you look at the photograph underlined. Otherwise, it won't be as detailed as possible. But that's a really good point. So I recommend tonight you stop studying and then you go outside at nighttime. And depending where you live, you might have to hike up a mountain and look up at the stars and find a nice star and try your best to look at it directly on and discover that it'll disappear. But if you look right above it or below it, it appears once more. So that's what I want to say about visual acuity. Now, let me move on to not that challenge. Yes, it would make a difference. However, it would drown out the stars because rods are very sensitive to light. So if that's the case, then suddenly everything will get washed out a little bit more. Okay. How do cones activate? Thank you for that question, Sophie. We're going to talk about that in this. Are we going to talk about that? No, we're not going to talk about that. I did make a note of where you're going to check that out so that how do they activate the cones? Did we talk about that? No, I think there's a point in the lectures that I'm going to refer you to so you can see the biochemistry of how they're activated. But it's really important that you look at that. Perhaps we can look at that in office hours because it is really important. But that's a more biochem thing, and it would not be asked in Psych Soc. So we're going to look at the next slide, which is no, I went too fast. Okay, so this part is a little tricky, but just bear with me as I try my best to explain it. So information is coming in the form of light to over 100 million receptor cells, both cones and rods. And so there's a concept that you need to know that's called a receptive field. And I wrote the definition there being that the retinal area of visual cell when the stimulation affects the firing of that cell. So I know it's a little bit complicated, but I'm going to do my best to explain it. So what this diagram shows over here is that you have the light hitting these different rods and cones. I'm going to annotate this one so that you can see that, let's say light hits these sections of rods. You can see that this bipolar cell is responsible for funneling all of that onto one single nervous cell, the ganglia. That's important for you to realize that that's a deliberate thing that this illustrator did. In the case over here next to it, you can see that to the right, that there's one cell that goes directly to one ganglia. It's a kind of one-to-one. But next to it, there's this funneling. Cones are also do that. They don't necessarily go one-to-one, but more often than not, it's going to be rods, lots and lots of rods that are funneled into one. So that is what we're going to call a receptive area. This area that I've circled in red is a receptive area that goes for one single rod. So let me X out of that. So the you can think about it as a sort of like as like a branched flower. It has one stem, but it's very branched up, and the top parts of the branches are the ones that receive the light, and the bottom of the stem is where the information is sent off via the ganglia. Um, so here is another way to look at it that is specific to the receptive field. So in this example to the left of the diagram, it's showing a type of receptive field that is quite common. It's called the center surround one. It's in the bullet point over there in the shape and size. It's called a center and surround arrangement. And so this is one of the examples of types of areas. And for the MCAT purposes, what you need to know is this type of shape, which is a center and surround. And then yeah, Tiffany, in the email, I explained that because of animations, this one would be messed up. So for this and wherever I have animation, I apologize, but you'll have to write it on the other side, on the side. So for this particular diagram, look at the screen instead of the PDF. Light is going to hit in this middle example into the center of this area. So remember, the area corresponds to one ganglia, as you can see in the bottom, but in the example in the middle, it excites the middle one in the center, and that sends off a signal. This ganglia to the right of that, at the far right, excites one of the receptors in the surround area of that ganglia. And it has, in this example, an inhibitory process that then, as you can see in the little box that has the neuronal impulses, it has far less neuron firing than the one in the middle. What is the important takeaway that you can understand from this one concept of receptive fields is that they're a key function in allowing for contrast and identifying edges. So what light does, for example, in the green, is that it tells you that there's specific amount of light. But let's say in the right-hand example, light hits the red receptor, it tells you, it turns off the excitation, which in turn begins to create an edge around there. So if you can kind of imagine, let's see if I can best explain this, as like you're seeing a color, and when that light hits the center one, it's going to be bright there and you know where the color is. But as the light also hits the surrounding area receptor, then it's going to turn off that color slightly, and then you begin to see an edge. Okay, tell me if you understood what I just said. Nobody? Okay, cool. Yes, that's the right response, bro. Can I repeat? I'm going to repeat this one also at the end of the lectures, because the concept of lateral inhibition. Yes, that's something like this. We'll talk more about lateral inhibition when it comes to pain. And I wish it were the same thing, but it's slightly like that. And so instead of thinking of them as equivalent, for now, for this slide, I want you to think about the key. You're going to read the word receptive field. And I want you to think, instead of having the definition, I want you to think of the key functions of the receptive field. They're responsible for contrast, and they're responsible for the edges of objects. Yes, Zoe, you can. Yes. In neuronal speak, you can. It's quite complex in the perception of it, which we'll talk about in a second. But yes, that's correct. And I think that if I'm thinking what you're thinking, that's the basis of what this slide says. I'm going to show you one more picture in this slide and then move on, which is this one, which shows you that receptive fields are small when it comes to the fovea. And as you get farther from the fovea, they become really big. So this diagram I really like because it shows you that cell number one is in the fovea. And why does it have a cone? Can you tell me why that's a cone and not a rod? You better tell me the right answer. Yes. Yes, 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 yes. Yes, yes. Okay. And then for cells 2 and cells 3, they're only rods because rods are found in the periphery. Perfect. Oh, Dominic. Oh, good. I'm glad you made this mistake, Dominic. This is something I was hoping somebody would make the mistake. So thank you for doing that. Cones are not only found in the fovea. Yeah, exactly. The fovea only has cones. Very important distinction. Cones surround the fovea too, but the key thing is that the fovea only has. Perfect. Thank you for making that mistake. All righty. So this is an interesting thing. I just want you to realize that these areas grow bigger. This is kind of like an aperture on a camera. Brooke, I think it is. I'm so bad at cameras, but basically a camera is an eye, except that it like you have to manually move it, whereas the eyes do all the work by itself. But I think you're right. I just don't know the cameras really well. Okay. All right. So let's move on. Oh my gosh, I need to hustle. Okay. So these are visual pathways in the brain. So we've talked so far, believe it or not, only we've gotten to the part of the retina and what happens with the rods and the cones, but we haven't talked about the rest of the visual system. So there's the axons that travel down the optic nerves. Now, this photo is really important for you to realize a couple of things. This stuff is gonna get tested the hell out of you for sure. All right, everybody, look at the left visual field in this diagram. It's nice and purple pink. Look at the right visual field. It's nice and blue. Everybody tell me, on which side of the eyeballs does the left field go? The left field goes to the right side. Correct. To the right side of the retina, also called the right hemiretina. Hemi means half, so the right half of the retina. Follow the left field lines and tell me on which side of the brain do they land when they go to the occipital lobe. To the right. Okay, now tell me the right visual field. On which hemiretina does it land? Retinas, I should say, because you have two. Correct. On which side of the brain does it land? Perfect. Okay. You think it's simple, but you're going to confuse it. And I'm about to help you make that confusing. Okay. So the left visual field and the right visual fields are contralateral, meaning that where they end up in the opposite sides of where they start. That's great. Perfect. Now, tell me though, when it comes to information from, oh, let me get this straight because I'm already getting confused myself. To the right, yeah. See, I'm already getting this stuff confused myself. Okay, this is the part that's confusing, which is the stuff from the left visual field ends up on the right side of the brain. It ends up hitting the right sides of the retinas. But do they travel on the right sides? I'm not even going to ask that question. You know what? I can't even ask it. So I'm just going to explain it. So what I was trying to get a question out of, but I'm not even going to attempt, is the fact that you have these optic tracks that once they hit the retina, they go down and they hit this optic chiasm. Thank you. It's called the crossover. That's exactly the point of confusion. It's confusing not because you see this diagram and you find it confusing, but because so many of the senses cross over the brain in different ways. So you're going to start getting confused as to which ways are crossing over. Exactly. And that's where I want to try to get the question to come out of Iman, exactly that, which is which sides are, yep, everybody's saying the right stuff. Yep. But I want to focus on what Iman said, which is that not everything crosses over. The things that hit the temporal side do not cross over in the optic chiasm. Got that? Temporal doesn't cross. Nasal crosses. So if you don't know what I mean, look at the diagram. In between the eyeballs, there's a label that says nasal. That means that it's the nasal side of the retinas. Why nasal? Because they're both nearest the nose. And the other ones are temporal because they're nearest our temples. So the nasal stimulus is the one that crosses over. So why might this be important? Can anybody tell me why the fuss about doing this? The crossing over part. Brain damage for sure, but yeah. Michaela, I like your response. That's how I feel too. Brain damage for sure, but more importantly, think about eye damage. Here's something really interesting that you should definitely write down. Because of the fact of the crossover effect, it means that if you get hit by, I don't know, your best friend finding out you're going through their text messages, right in your one of your eyeballs, and it swells up and you cannot see, because of this crossover at the optic chiasm, you are still able to send messages to the right side and the left side of your brain. I should expect like jaws to drop at my answer to that. Yes, thank you, Brooke. This is one of the most important things you need to memorize about this slide, is that this mechanism exists precisely for the fact that we have two eyes, but if we didn't have both, then we shouldn't be able to lose one or the other visual fields. Got that? Okay, write that down. I'm going to move on. So that answers the question of why the arrangement. There's two visual. One more time? Okay, great. If you lose sight in one of the eyes, Jonathan, let's say you lose sight in the right eye in this diagram. Your left eye, does it get input from the right and the visual left field? Say yes. Yeah, okay. Now that visual input from the left eye, because your right eye is puffed up and you can't see out of it, where does the right visual info go? To what side of the brain? And the right and the left vision and the oh shit. And the left visual field input, what side of the brain does that go to? Precisely. And you did that from one single eye. If this crossover didn't exist, you would only be able to see on one side, one visual field, and your brain would not receive the other half. Perfect. You'd be half blind. Precisely. So keep that in your mind. Write it down. Don't forget it. Let me talk really quick about the two pathways. There's this really awful word called the retina geniculate striate pathway. And basically, we're just going to call it the LGN pathway. The LGN pathway is the one that follows the dark lines, not the dotted lines. And it's called that pathway because the optic nerves synapse, both the temporal and the nasal one, synapse in the lateral geniculate nucleus, which is in the thalamus. And Tiffany, thank you for bringing that up. I'm going to, yeah, y'all are stealing my wind for sure. So it travels down there, and all you need to know is that it goes right there. The second pathway you need to know is the superior colliculus pathway. In this diagram, it's done in the dotted lines. The reason why you need to know the second pathway is because, as you can see, it doesn't travel to the occipital lobe. It goes through other parts of the brain and the limbic system. And this has to do with motion and coordination. So everything that goes back to the brain, think about as like what we end up perceiving as seeing, and everything that goes into the synapses right there is going to be the stuff that it tells us where we're seeing it and the motion that that thing has. No worries, Tiffany. No, I realize that. But Tiffany sent me a message that is really important for you to know, which is a term that you need to write down, which is not in my note. What? Oh my gosh. Which is that that when we're talking about how input from stimulus goes to different sides of the brain, that's going to be something that's called contralateral. Let me write that down. Contralateral lateralization, basically meaning in everything on the that starts on the right side makes its way to the left. And if something starts on the right side and remains on the right side, it's called ipsilateral lateralization. I think I'm going to talk about that in the next slide. And if not, I'll go back to that concept, but just keep that in mind. There are types of lateralization, right? These are types of lateralization, and different sensory systems have different types. They employ one or the other. In the case of the eye, we see both. I think I will go back to that. Oh wait, no, I'm sorry. It's in the past slide, right? Oh, I'm so sorry. The second bullet point and the third bullet point say that the temporal messaging is on the same side. So this is what you need to know about this slide too. So the two things I said about optic chiasm, I said the optic chiasm is what you need to know. Also memorize that temporal messaging is ipsilateral. I like that. And nasal messaging is contralateral, which is what we've already talked about, how the stuff on the temporal side remains on the same side of the brain, stuff on the nasal side goes to the opposite side. That's all. Okay. So information in the brain. So this is one of the messy slides, I apologize. But you just got to know a couple of different things about the pathways once they go through the LGN pathway. So remember the one that's the solid line. When they're in the LGN, not when they're in the occipital lobe, but when they're in the LGN, which is in the thalamus, two things happen. They subdivide into something called the parvocellular pathway and the magnocellular pathway. 80% of the neurons go to that, the parvo, 20 to the magno. Sorry to say this, but you need to know this. I don't know why, but you do. But you need to know in a very basic sense. Parvocellular activity is responsible for that input to activate cells that tells us about where, what the visual input is. So spatial resolution. So say parvo is what? Magnocellular activity is responsible. Yes, Jonathan, that's correct. Magnocellular activity is responsible for temporal resolution. In other words, movement. So think magno motion, period. That's all you need to know. But you need to know that. You need to know that in the LGN, there's these two pathways. One is responsible for the what. Interestingly, and not surprisingly, 80% is dedicated to the what. And a lesser percent is dedicated to the motion, the where. So I like to think magno motion. Information pathways are are then later, those two pathways meet one more time in the occipital lobe in a place called the visual cortex. So there's the occipital lobe, which is a section of the brain, and then there's a subsection within the occipital lobe called the visual cortex. And that's where all these different stimuli that we've been talking about, different the what and the where of particular visual stimulus, meet in a process called parallel processing. And that way, what we experience is all of these things coming together so that we're not only figuring out what it is, but we're also figuring out its aspect of motion. It's called parallel processing. And you need to know that. And yeah, so Aditya, you need to know not the crazy steps. All you need to know is what I've said, which is that LGN subdivided into these two pathways. These pathways then meet in the visual cortex in a process called parallel processing. You need to know that. Parallel processing processes at the same time color, form, depth, and motion. Pretty straightforward, right? I think I missed one detail here. And then the primary visual cortex have very specialized detectors. They're called feature detectors. So all you need to know about this part is that the visual cortex have these things called feature detectors, which I have italicized for you. They're important, so I've given you the definition for them in the italics, which is that neurons that respond selectively to very specific features of more complex stimuli. It gets really complicated in cognitive psychology when you're talking about feature detectors. So let's just say that you focus on the fact that these are cells that respond to specific features of visual stimuli. For example, they respond to the lines at certain angles. That's all you really need to know for that one. Just keep that in mind. So here is that once the information is processed in the primary visual cortex, it then continues to go on, because the primary visual cortex is the one that's going to, as we've talked about, tells us about the stimulus and the what and the where. But then they have to go into different parts of the brain so that then we can have nice feels about it, right? Like you can have everything that we've talked up until this slide tells us how we can see our friend. But until we get these other pathways shown in this slide, we wouldn't be able to feel warm and fuzzy things toward the friend. So I hope you understand that up until the visual cortex, we've understood the image, but we haven't yet registered it as emotional. And that's where these streams come in. So we have a ventral stream, which is the what, which is then we start getting sensitive to faces, for example. And we have a dorsal stream, which is the where. The ventral stream in the diagram is the one in light green, and the dorsal one is the one that is in the red. These are going to different parts of the brain. The sections they're going to are the parietal lobes and the temporal lobes, which you probably talked about yesterday a little bit in the neuroanatomy part, hopefully. So all you need to know about these pathways is that there's a ventral and a dorsal stream, and you need to know the main concept of it, which is the dorsal is the where is the thing, and the temporal is what is the thing. Do not confuse these with the parvocellular and the magnocellular pathway. Do not. Tell yourself you're not going to confuse them. And maybe you still will, but try your best. All right. So believe it or not, we've talked a lot about this stuff. No, Tiffany. Parvo and magno meet at the visual cortex, and they just meet there and they mingle and they come together. From there, new streams come out to the ventral and the dorsal. Yeah, exactly. They're not equivalent. The parvo, because we said that magno is motion, and we spoke about the where stream. Those are not equivalent things though, but I think you understood what I'm saying now. So believe it or not, we've only talked about the perception of sight, but we haven't really talked about color. So the MCAT loves color for some reason. But here I'm going to talk about two different theories of color. So the first theory of color that we're going to talk about is the trichromatic theory of color. And then I'm going to talk about another one in the next slide. And believe it or not, these were both discovered in the 1800s. It's like, wow, people in the 1800s actually like figured out stuff. And they figured out stuff without actually having like fancy instruments and actual knowledge of like neurons and stuff like that. They figured it out by the deduction of what just observations, which is kind of cool. In the trichromatic theory of color, this guy named Helmholtz, don't memorize it, figured out or said that we have three kinds of receptors in our retinas. So take this, you know, when you study Mendel and you're like, he was going off of pea plants. Well, he's going off of some things that aren't the cells. So instead of getting confused of like, oh, which the rods or the cones, take it more like, okay, this is a theory that was formulated before rods and cones were understood. But it turns out that some things are right about it. So that's why I preface, like, don't try to mingle too hard the biochemical things of cones and rods with this theory quite yet. So there's three kinds of receptors. There's the red, green, and blue receptors. So basically what he's saying is that our eyes somehow have receptors that are sensitive to these three colors. It turns out that there is support for this theory. One is color blindness. It turns out that color blindness seems to show up primarily in people having a hard time detecting red or green or blue. Blue is the rarest of them. Red and green are more popular ones. Here in this diagram is a really nice example of what somebody with a red-green insensitivity color, they're called dichromats, would see from the pictures. So unless, pardon me if anybody here is colorblind to red and green, you would then see different pictures. So the majority of us, more likely than not, will see different photographs of there. But it's kind of a trippy thing for people who don't have color blindness to be able to kind of detect what it would look like. And as you can see in the bottom images for those people who don't have color blindness, is that it's kind of trippy, like how they look exactly the same. At least I find it very interesting. So that's a support for the color theory. Another support for it is that color theory, for this theory is that that we see that there are genes in the X chromosome that code for the sensitivity of these three colors. So this is obviously discovery way after the fact of this theory being postulated. And it's most frequently expressed in males. Can you tell me why that is? Not homozygous recessive, sex-linked. X-linked is sex-linked. Another thing you should write down and like get tattooed on your arm. X-linked is sex-linked. For the MCAT, you will not see any sex-linked disorders that are on the Y chromosome. Men have XY genotype. Women have XX. And so if you have a mutation on, if you're a woman and you have a mutation on the XX, on one of the X or the two X's, then you can still express a normal phenotype. In men, it's genetically impossible. Always glad to throw in genetics whenever I can. JK, no, I don't like genetics. Okay, so here's the other theory I was talking about. Oh no, JK, it's not the theory. It's more on the same theory, which is that it also supports the fact that we have complementary after images. So I want you all to look at this watermelon, focus on the X. Look at it. Don't type into the box if you're looking at it because you're just staring straight at the watermelon. A little bit longer. Don't blink. Your eyes should hurt. Water. Okay. Do you see an after image? Yes. Okay, good. Sad. Yes. So the factor of the correct watermelon. I don't know what you're saying, Tiffany. I thought the other one was perfectly fine. Um, but I would eat it for sure. Yeah, blue watermelon, bye bye. Um, so the after image is something that the after image is something that is supported that supports the trichromatic color theory of vision. It turns out that these receptors, like was postulated at the beginning, were really good about um, activating a certain receptor. So in the case of the watermelon, the blue, as you're staring intently at the blue, it's activating the opposite receptor, which is the red one. No, it's inhibiting the red one, excuse me. And vice versa for the red one, you're staring at it and it's inhibiting the green. When the after image goes away, the inhibited one shows up. That's all you really need to know about this, that it supports the trichromatic theory. Um, the other process that comes up is the opponent processing theory, and it came up like 10 or 20 years after the first one I talked about. And this one is pretty interesting, but it says no, we don't have red, green, and blue receptors. You're wrong. But we have receptors, and some of them are sensitive to red versus green. Some of them are sensitive to blue versus yellow, and some are sensitive to black versus white. So, so what this one is saying is that instead of us seeing activating only specific colors, we activate these receptors that when you see the red, you deactivate the green. And when you see the blue, you deactivate yellow. Notice that it's important that this one doesn't have three colors. This one has four colors: red, green, blue, and yellow. So that's one way to kind of think about these differently. And it also has black and white. And one of the ways to prove that this one, or support it, I should say, is that I can ask you to come up with a description of colors that are mixes of red and green, of red and yellows, or colors that are mixes of green and blues, or red and blues and green and yellows. But if I ask you to come up to describe a color that you've seen that's a mix between red and green and blue and yellow, you'd freak out. Your brain would break, right? You can't think of anything because you haven't perceived a combination of blue and yellow or red and green, have you? Say no, you haven't. I'm not talking about putting them side to side. I'm talking about a gradient. Yeah, you're forced to say no. Thank you. Right. Blue, Sophie, just to make it clear, what you're doing there is adding two colors, which is totally allowed. But what I'm talking about is a gradient of like, can you imagine like a blue yellow? And you can't. Um, so, so that's what supports this opponent process theory. Okay, that's all I want to say about that one. So there's now we have to put these two theories together, and so they actually it turns out that they're both right, and in certain respects, and they both actually work together. So now we have evidence that shows that we do have cones. Now we're talking about actual cones. Before then, we were just talking about theoretical receptors. Now we're talking about cones. And it turns out that cones, as you can see in the diagram, have varying sensitivities to colors. And they peak in their sensitivities, some of them in blue, some of them in green, and some of them in red. So it's like, well, Helmholtz was right with the trichromatic theory. Michaela, as I was saying that, thank you for pointing that out. I have confused myself, and I think that was support for the trichromatic theory and not support for the, excuse me, support for the opponent process theory, not support for the trichromatic one. I'm gonna have to clear that up. I made such a fuss about the blue watermelon, and I'm not sure anymore. Let me get back to you about the blue watermelon. Yeah. What I'm saying, Tiffany, is that I might be thinking the opposite way, that it supported opponent process theory. The blue watermelon is actually there more for fun. So, so I'll get back to you on the correct thing. But what you need to just distinguish is that there's two theories: trichromatic and opponent process. And from this slide, we can see that they're both kind of right. Uh, so the way that the trichromatic theory is right is because we've discovered that rods actually have sensitivity to those three colors in these peaks. The way that we know that opponent process theory is correct is the last bullet point, which is that we've discovered in the LGN and in the visual cortex that there are cells that respond in opposite ways to when they receive red or green or blue and yellow. Boom, they're both right. That's all you need to know. All right. Let's, any questions about this before we move on to the perception part? Oh my gosh, how am I going to do this in 20 minutes? Dear Lord. Okay, I'm moving slow. The graph just says, Tiffany, that we have cells that are, that's actual discovery of rods, sensitivity to those three ranges. So imagine that there's three groups of rods, and one of them is in one mound, and another group of rods is in another mound, and the other one's in the last mound. The groups in the first blue mound peak at blue, meaning that that's where they're most sensitive. And then their sensitivity trails off as you go up and beyond that peak. Does that begin to make sense? And if not, I promise I could go back. If you just make a little note, we can talk about it. Yeah, I promise we will talk about it. And I'll do a better job of clarifying it. Okay, so don't ask any questions. Let's move on. All right, so let's move on to the visual process system. So far we've talked about, no worries, Tiffany. No, I understand. If you have the question, likely most people also do. But I promise I will clarify. So the perceptual process is something that we haven't talked about. So we talked about actually everything that we talked about so far, believe it or not, is about stimulus and objectively how that impulse is carried from stimulus to impulse in the retina all the way throughout the brain. We actually haven't talked about the perception of it, which is what we talked about at the beginning when I asked you what the difference is, which is like the subjective part, which is how our brain interprets all these different neural impulses. So now we're going to talk about perceiving forms and patterns. And this is another ugly slide. I apologize. But I'm going to start off by, so yeah, the sensory experience is objective, whereas the other one is sensory perception is subjective. And I'm going to start off by talking about a perceptual set. So the perceptual set, the definition of that is the readiness to perceive a stimulus in a certain way. Got that? The readiness to perceive the stimulus in a certain way. You can kind of think about that as a sort of expectation. And I'm going to show you a diagram of a really nice poster that I found. I'm from the Bay Area, so naturally I'm very in love with seals. And I found this really cool poster of a training for seals for a circus, because I just think they're the most cute and adorable things in the world. Yeah, don't you like this poster? But wait, is that really a seal? Or is that like a masquerade ball and some hand is like holding somebody romantically? Michaela, there's also theories as to why you thought that first, which have to do with sort of more of like a particular preference of looking at a certain thing. Oh, you don't see the seal? Oh no, you still can't see the seal? Oh my gosh. It has the head for the woman is a ball bouncing on its nose, and instead of like a little droopy thing on her arm dress, it's actually a fish. Oh gosh. So what I was trying to do, and I apparently seemed to fail at, was to set an expectation, aka a perceptual set. I was trying to tell you a little story about how I like seals, and y'all saw a woman instead. Oh my god. Okay, cool. Priming, yeah, priming is like that. but thank you. It didn't work. I know. Priming is like that, but we'll talk about priming when it comes to the aspects of languages. So for this one, think about perceptual set, not so much as like, um, don't think about it priming. Think about it more as terms of like, we're still focusing on sight. Priming can be something that can happen for language. It could be happening for all sorts of things, but we're still focusing on vision. Um, Thank you. Now you can't unsee the seal. Okay, cool. Good. At least I'm glad you see the seal. The second thing I want to talk about is selection. This has to do more with like people insisting on seeing the masquerade ball first, which is what people focus their attention on. So selection is the same process that's happening right now with Alexandra, who can't unsee the seal. You're selecting certain things, and the other things are impossible to make you go back to go see the masquerade. It's an effect that is happening, and it's related to something, or rather, it's demonstrated in something called inattentional blindness. Notice that's an italicized one, and I've given you the italicized definition because it's really important, which means that Alexandra, as hard as she's trying, is failing to see anything but the seal because the attention is focused so much on what the seal is. I'm sorry to use you as an example so much, Alexandra. But unintentional blindness is, that's right. And I have other examples like that. Inattentional blindness is something that was famously done an experiment with the basketball video where they asked viewers in the test to look at this video very intently as seeing the ball following as they're dribbling the basketball game. And they're asked to really follow the ball moving around. Unbeknownst to the viewers, or about to 80% of them actually, a gorilla or a guy in a masked gorilla walk through the whole thing several times and they didn't notice it. It's a very famous video and I encourage you to watch it because it's kind of incredible that they wouldn't see it. It's hard to experiencing yourself now that I've told you this because of selection. But it's something that if you weren't told about it, that you might be a victim to inattentional blindness. These other slides are also have quite a few terms that are very important. This one in particular has terms that I think I want you to have as a big takeaway of the processing section. One of them is feature analysis, which is that the process of detecting elements in a visual input and assembling them into a complex whole. This is so important that you memorize this term. The diagram does a really good job about describing feature analysis. So it looks at the letter T and it says that that's what hits the retina, and feature detectors, which we've learned are cells in the visual cortex. Some of them are responsible for detecting certain lines at angles. So this is where finally it's coming back, and hopefully you remember a little bit about it. And so they detect lines in certain angles. As you can see, the ones that are highlighted in orange are selected, and then there's different options of what they could possibly be, but they all match a T. And so then the decision is that it's a T. So that's feature analysis. Feature analysis is it is something that's a proposition of how our brain works, that we put together pieces of different visual stimulus using feature detectors so that then we can come up with a whole. This model has an assumption though, and it relies on bottom-up processing. Bottom-up processing is really important, and you need to really know that term, and that it's a process that involves of putting together making up an element from processing things from individual elements to a complete whole. So the name is pretty self-explanatory, but it's super important, you know it. And basically it's doing bottom-up processing is what this is showing in the diagram, is that you're going to put together different elements such that it spits out the letter T. And so that's one of the assumptions. The other assumption of feature analysis is that you detect features and stimuli and build them into recognizable forms. So again, what the T is showing. And what is the support for this model? Feature detectors. We've discovered that we actually do have these neurons in our visual cortex in the occipital lobe. But there's an opposition, obviously, to that model, which is the fact that we know that things aren't always bottom-up processing. For example, look at these diagrams on the right-hand side. Tell me, what do you see? What shapes do you see? Thank you, Jonathan. You're so wrong. Obviously, there's no shapes. There's like a little square looking weird dot. There's like a little, there's three Pac-Man. Thank you, Dominic. Exactly. No, I'm kidding, Jonathan. You're absolutely right. There are these shapes that are intuited. We totally see a circle and we totally see a triangle. Ah, okay, good. You're getting ahead of me, but that's right. Gestalt principles talk about this. But for now, this slide is showing that no, we do detect circles and we do detect a triangle, and it's not bottom-up processing, because if that were the case, then all we would be able to see is a bunch of Pac-Man. So this is actually the opposition to it, which is that there's top-down processing, which is so important that you know, and it's the opposite of bottom-up processing. And top-down processing means that you're progressing from the whole to the elements. So we most likely all saw a circle and a triangle before we saw Pac-Man and little bricks. So memorize top-down processing as well. There's evidence to the fact that we do it, not just the fact that we just saw it with this surjective contours. That's the formal name of this exercise we just did. But there's also perceiving words before letters, which is a concept. Excuse me, you don't need to know the name, but it's called word superiority effect. And you see it all the time when you typing something really fast and you misspell something, but the word looks right and you can't find the mistake in it. That's because of top-down processing. So it's so important that I put this slide. So once more, bottom-up processing is that you go from a stimulus and you recognize the different elements that make up a complex whole. Top-down processing works in the opposite way, where you have already a hypothesis about what something is, and then you break it down into its individual forms, and then you end up recognizing the feature. All right. So not much to say about it except really know this. Really know this. So now we're going to get to what Jonathan is super antsy to get to, which is Gestalt principles. Gestalt principles are really pleasant because they're a branch of psychology that's like focused on top-down processing. It's like they can't get enough of top-down processing, and they have to like come up with so many different principles. The fun thing about for the MCAT is they're pretty intuitive, and I think they're kind of fun. And I don't suggest you memorize them. I think that you should recognize them though, and they can be kind of fun, and sometimes it could be tricky, but I think it's a recognition thing. The idea behind Gestalt principles, or laws, as they're also known, is that there are properties in the whole of the stimulus that are not found in their individual parts. One example is the phi phenomenon, which is that something like the one in this diagram is telling you there's motion to it. Our eyes are drawn in the direction of the arrow, and what it's saying is that if you were to take out different elements of this whole thing, you would miss the motion. And that's because it's an element of the whole and not of the individuals. So think Gestalt, top-down processing. Write that down. Gestalt, top-down processing. So we're going to go through a couple of them. And these are lovely to look at. Figure and ground. So we have a figure and we have a ground. And in fact, most Gestalt principles focus on the figure of it. And the figure is defined as the thing that we see the closest. And the ground is defined as the thing that we see as the backdrop and the farthest. Sometimes when we're looking at these ambiguous images, though, it's pretty fun to realize that when they're reversible images, when we can't really figure out which one is the figure or the ground in this case. Obviously, this diagram that I'm showing you is a picture of a goblet, right? like there's no other thing, and the background is just negative space. Faces, right? Exactly. So it's actually ambiguous, like Brooke's saying. Like you could see one or the other, and using a process of selection that we talked about, you can kind of fixate your attention on one or the other. But the thing here that's interesting is that there's not enough evidence to tell you that one is definitively the figure or one is the background. Proximity. So now we're going to focus on the rest are kind of like figure focused. So the proximity ones are pretty interesting, which is saying that when particular figures are closer together, we think about them as units. So I could tell you that this is a diagram of a bunch of rows of dots. Excuse me, I could tell you I said the wrong thing. I could tell you that this is a diagram of a bunch of columns of dots. And you would say, hell no, it's a bunch of rows because of proximity. There's closure, which is one that we talked about with the Pac-Man, the bricks. And here is the fact that the objects that are coming together in certain ways suggest closing of the lines between those objects, such that we understand an image as a whole. Similarity is one that's kind of interesting and easy to confuse. So I like that one. Similarity has to do with that objects or stimuli that are similar to each other become a unit amid the rest of the stimuli. So in this case, darker spots are contrasted from lighter spots. And so we think of the darker spots as being a whole. And so we see the letter 2. Law of Prägnanz. Prägnanz, Jesus. I don't know why we keep on calling it, but I guess it's because we don't have a really good translation for this term. Prägnanz translates from the German to mean something like good form. And you can think about this as simplicity. So this one's actually kind of tricky for me sometimes, but if I look at this image, it's kind of like a squat, like a modern painting that's like a gum on the sidewalk or something like that. But once I tell you that it's a triangle overlapped with a rectangle, you can't unsee that. And that's because of the law of Prägnanz that says that we tend to perceive the objects as something in its most simplest form. You can think of Prägnanz as pragmatic. Continuity. This is the one that kind of looks like the 5 phenomena that we talked about, which is that objects in a particular way that are arranged in space seem to tell us that they generate a smooth path, or like rather, I should say, that we have the tendency to perceive objects that are close together as following the smoothest path possible. Yeah, that's a better way to describe it. And that was it. Yeah, I can definitely go to closure again. Closure is this one. And the idea is that we have a tendency to complete figures. That's all you really need to know about that. And that there's actually gaps in things, but we want to complete them as best as possible. So, okay. So far we've talked about the Gestalt principles in terms of how we organize visual input. But we haven't talked about something really interesting, which is a perceptual hypothesis. And I realize it's 11 o'clock now. My God, time flies. And my goodness, I have so many slides left. Oh my God. I'm going to try to breeze through as much as I can without missing the essentials in the next 10 minutes. I apologize about going over. And then we'll see where we're at in 10 minutes, and then we can figure out some other things. So sorry about that. And Tiffany, I'll get to that at the end, just because I'm clearly out of time. So perceiving the forms, we've talked about how we went from 2D images, but we haven't talked about how we get to 3D images, believe it or not. This image over here does a better job of explaining what I mean. So this person is staring in the first, in the left-hand side at a square paper, um, and this person is looking head on to the paper. And so the thing that hits the retina is actually a square. I hope that makes sense, that the thing that's hitting the retina as a stimulus is a square that's projected onto the retina, and then that is projected onto the visual cortex in the occipital lobe. As the person moves the card farther from their vantage point, you can see in the following two images that it becomes more and more trapezoidal. However, so the trapezoid is hitting the retina. I know it's a small distinction, but it's really important to realize that what's hitting your retina is actually a trapezoid, but what's actually the thing that you're going to perceive is still a square. I hope that trips you up a little bit. And the mechanism for doing this is one that's called the perceptual hypothesis. And so that's one possible way for how to explain this. And so the perceptual hypothesis, and you need to write this down, is a perceptual system that guesses, quote unquote, guesses that the trapezoidal image on your retina is actually a square. It's really important for you to realize that as we look around the world, not the things that we perceive to be particular shapes are actually hitting our eyes in very distinct ways. So I hope that makes sense. So here's a definition for the perceptual hypothesis. Sorry, you didn't have to write that down, but that's a possible explanation that explains this question mark gap of how we go from distorted 2D images to actual 3D representations. And then perceptual hypotheses are not always possible, though. Let's see, what did I want to say about that? Oh, right. So sometimes expectations really influence the way that we will perceive an object. For example, quite like this reversible figure of an old babushka wearing a fabulous fur coat with her nice head wrapped. Or as some of you are going to tell me now instantly, like, oh, wait, is it a woman who's looking away? This reversible image obviously has a surprising thing about the ambiguity, and that you're not able to figure out which one or which of it is or which it isn't. So that's where context effects, which is this italicized term, comes into effect. I think context effects is something I can better explain with this next image that has a nice animal on, or not animal, but the writing of an animal. So obviously everybody sees the cat, right? But JK, can you tell me, is there actually any difference between what you perceive to be the H and what you perceive to be the A? No. Yeah. This one, hopefully, this one of all the ones I've done, hopefully this one tripped you up. But yeah, the H and the A are actually, or what we perceive as H and A's are actually not different shapes. They're exactly the same ones. But because of context effects, we find that the context in which we see certain things affects our perceptual hypothesis. So that's all I want to say about that slide. And that this is another example of top-down processing. Oh, and I told you that. Now I'm going to talk about depth. And depth perception is, for some reason, something you need to know for the MCAT. I've given the definition here, which is the interpretation of visual cues that indicate how near or how far objects are. There are two types of depth perception. It's the binocular and the monocular depth perception. They're really easy to confuse, but my tip, and I swear to you, you'll stop confusing them, is that binocular, there's two depth cues for binocular, and the rest that you're going to see are going to be monocular. If you don't realize that, then you're going to start getting confused as to which one are binocular and monocular. So bear this in mind. There's two for binocular that you need to know, and everything else is going to be monocular. Binocular depth cues, as the name suggests, require both of your eyes to do this. So in the example I gave earlier of being punched and blinded out, you would lose the ability to have these binocular depth cues in that case. And there's two of them. There's retinal disparity and convergence. Retinal disparity has to do with the fact that our retinas see different objects. Different things are projected onto the retinas. That makes sense because our retinas are angled at a certain way in our eyes where we actually don't see exactly the same image projected. However, it's still projected as one individual image in the brain. The thing to realize about retinal disparities, it has to do with retinal impulses, and that the closer that the object gets to your line of vision, the greater the disparity between those two images. Convergence is something that can easily be confused, but one thing that'll help you not confuse it is that convergence is a muscular thing. It has to do with the fact that it's a neuromuscular effect of as objects come closer to you, your eyes have to turn inwards. And so the muscular effect of having your eyes move inwards has a lot more muscular tension. And that muscular tension is sent back as information to your brain saying how far something is from you. So it's an interesting mechanism and it's different from the retina. The retina one says these images are very different, which means that they must be close. The convergence effect says my eye muscle tension is great because they're converging, therefore the object must be close. So yes, if that made sense. No, accommodation is, remember we talked about the lens of how the lens gets rounder or flatter. And that's a property of each one of the lenses. For binocular depth cues, we're talking about things that both of the eyes contribute that send information to the brain. Correct, Sophie. The closer the images are to the eyes, the more different the images projected onto the retinas will be. So now the monocular depth cues. So these, like the Gestalt principles, you have to recognize them, but I stress, don't worry about memorizing them. And they're pretty straightforward. I think the most confusing thing about them is not confusing them with binocular depth cues, but you won't do that anymore because I've told you there's only two, which is retinal disparity and convergence. The rest you're going to know that monocular depth cues happen. It's a good thing we have depth cues with one eye because if we lost one of the eyes, then we wouldn't be able to see depth. So this is another reason why we want to have systems working for different circumstances. I'm going to go through these, and these are pretty self-explanatory. So the depth cue for linear perspective is that as two lines that are parallel, as they go forward and converge and become one line, means that that line is getting farther and farther away. Texture gradient means that the closer you are, it means that you see closer detail. And the farther an object is, you see less detail. So you see more fuzzy bunny rabbit fur, and you don't see any of that in the farther ones. Interposition is one in which if you have objects standing in the way or partially occluding other objects, it suggests that the ones that are doing the blocking are closer to you than the ones that are being blocked. Relative size comes into play when we understand, this is an understanding part, that the objects are of the same size, but the ones that are farther away look smaller. So it's something that even though we know that they're of the same size, the farther away ones appear smaller in our view. Height in plane is one in which you have an object in a plane, such as the swan that's on the lake. And the closer they are to you, lower in the plane, it means the closer they are, the lower they are in the plane, the closer they are to you. So if we place the swan higher in the plane, it would suggest that the duck was actually farther, closer to the bridge. Swan, excuse me, that's offensive for a duck. And light and shadow. Need I say anything? Should I memorize the two eyes or two main characteristics? Both, Fabiana. Please memorize both. Binocular means that it's both eyes. That could be easily a trick question saying that somebody is experiencing a binocular view even though they have they're blinded in one eye. It would not be possible. So memorize that it's involving both eyes and that there's two popular depth cues. Is there, what do you think the moon is following you like the car? Yes, Michaela, that is something known as motion parallax. And I did not bring this up and I will have to bring it up, but it will come up better in the kinesthesia talk later. Okay. And then the last one of the section. Linear perspective, Sophie, is the one in which you have two parallel lines that as they continue to advance, they converge. And that is a depth cue that says that the point in which they're converging is farther than the one that in which they're parallel. So just think about that road. What the depth cue means is that the line as it becomes narrow and narrow and they converge, it just means that that point is farther than the ones where they're separate. I'm going to finish up by talking about perceptual constancy. And this one is, I've defined here for you as a stable perception in continually changing input. Because believe it or not, everything I've said so far has been static. We haven't talked about what happens in our visual perceptions when things actually move. We've talked about photos and perceptions, but as if it's a static world. I think this is best explained by an example. And so you're outside of a coffee shop and you're waiting for your friend, and your friend arrives late as usual, and she's wearing a bright red halter top that says "Free Britney," and then she arrives, and then you both go into the blue bottle, and the blue bottle is shaded, and suddenly her bright red halter top no longer looks bright red. Instead, it looks like a regular kind of dull red. Did the color change? Did the color of her top change? No, it didn't. And we don't perceive it as actually having changed. But the reality is that what the retinas receive is actually a different tone of the red because less light is bouncing off of it. But however, our brains don't say like, oh, her top changed color once we entered the bougie establishment. So instead, what you say like, no, it's still red. So then for that, perhaps that same friend, I'm trying to recollect the size one. Oh, excuse me. And then before you went into the blue bottle, for you were waiting for your friend outside of the coffee shop, and your friend arrives at the corner, and so you see the friend at the corner, and they walk, and as they walk, the stimulus that's entering your retina is one of a little short figure that keeps on growing and growing and growing. Instead of freaking out because your retina is sending signals to the brain saying like, my friend is suddenly increasing in size rapidly, it's saying like, oh no, it's the same size. She's the same constant size that she was. It's just that she's getting closer to me. Right, exactly. Right. The brain has to constantly think about these scary different things that are happening all the time and say like, no, calm down. It's the same size. Her top hasn't changed. Lastly, she finally gets her pumpkin latte frappuccino and then starts twirling in the middle of the coffee shop. So it's certainly a very strange behavior. But what's even stranger is that what's arriving to your retina is a person that's shape is changing as you see the different profiles of that person. So the what's actually arriving to your brain is somebody who's like turning and turning and turning, and each one of those profiles looks slightly different in shape. But the brain, however, perceives it as the same shape. So I know these are really subtle things, but they're going to come up in the MCAT, I assure you. And it's kind of confusing because as intuitive as they have in names, we don't actually can think about the logic behind them. So the idea behind perceptual constancy is that I want you to remember it means that even though the retina is constantly receiving different stimulus information, it tells the brain it's still constant. The subdivisions for it are three common ones. It's color, size, and shape. That's all you need to know, and they're pretty straightforward. We've arrived to the end of the section. I have to apologize because I realize how we haven't yet covered the hearing. So it is 11:16, and I think I can do hearing um, in 15 minutes or less because it's much shorter than vision. But we can post to this in our next office hours. My fear with office hours, though, is that I want it to work for everybody's schedule. Again, I apologize, but I hope I've done a good service of showing you everything you need to know for vision and perception. So far, I've got a few. Yeah, okay. Okay. Yeah, okay. We're getting a saying that we should do it now. Apologize again for this, but like I said, hopefully everything that you've seen in vision and perception, vision sense and vision perception covers absolutely everything you need to know. So let's go through hearing, and let's skip that part. All right, we're going to go to the auditory system. All right. So the stimulus is sound. Yeah, Maria, I'm not even covering taste and pain. And anyways, we'll see in a second. Let's go to the stimulus. So sound waves. So sound waves, what are they? Just someone tell me really quick. What are sound waves? It's longitudinal, that's right. They're waves of sound. All righty, perfect. More specifically, they are compressions and relaxations of particulates in whatever medium they are. So you might remember from physics. If not, then you're going to have a really crude awakening very soon of the complexity of how it is that air compresses when hearing things in air, I should say. Air compresses and then it relaxes. And this pressure gradient is what we end up transforming from a sound wave into hearing. I've put little emojis to say like what happens when you pluck a string. You're going to do lots of formulas of strings. Or you blow into a tube like a saxophone, and you're going to do those formulas as well. Or one that we always forget, which is like a sudden pressure change, which is when we clap or when we break the sound barrier after we go faster than the speed of sound. That also produces sound. So how are they psychologically perceived? So we talk about in light, if you can remember, we talked about the wavelength being hue. We talked about purity being saturation. And we talked about wavelength, purity, and what am I missing? And brightness being amplitude. I hope you remember. Now, what are the amplitude, wavelengths, and purity recognized as psychologically? Because of time, I'll let you know now what they are. But write down, if you will, that amplitude is loudness. Got that? Amplitude is loudness. Wavelength is pitch. And purity is timbre. That one probably is maybe a new term to some of you. Timbre. Alrighty. And then wavelengths of sound are often described as frequencies. We know from the universal formula for waves that this is how they are related. Oh shoot, I did that wrong. frequency and how do I do a lambda? Anyways, lambda, that one. Hopefully that rings a bell. Timbre is going to be the quality of the sound. And I'll talk about that in a second, but basically think about it this way of like how you have a violin and a cello playing exactly the same note, yet they sound completely different. It's the same frequency, but the difference in how it's perceived is due to timbre, which has to do with purity. So we talk about wavelengths in terms of frequency. Notice a difference in how we talked about light in terms of nanometers, which is a wavelength. We talk about it in frequency, which is measured in hertz. And hertz, as you probably know, is an inverse second. This diagram really quickly just shows a wavelength that's actually not as pretty for sound as it is for light. For light, there's a nice little oscillations, but in terms of sound, it actually can be quite complex. And that's all I really want to say about that. So let's talk about certain thresholds. So for seeing, we talked about the range of visible light in terms of its wavelength in nanometer measures. In terms of human hearing, what we're going to talk about is in frequency, and the lowest we can hear is 20 hertz, and the highest we can hear is 20,000 hertz. Got that? 20 to 20,000. Okay. And the sensitivity to this range decreases as we age for a number of factors, but those are beyond the scope of the MCAT. The amplitude of the wave we talked about as being the loudness, and those are measured in decibels. Decibels is something that you'll discuss a lot more in physics when it comes to waves. And those have complicated formulas that accompany them. Let's see. That's all I want to say about. Oh no, excuse me. Let me go back to this one really quick, which is going to tell us that the threshold for pain in this diagram where this dude in the yellow sweater is sawing, the threshold for pain looks like it's around 130 decibels. It kind of goes down a little bit as the frequency increases, which is to say the pitch of sound increases, but it kind of remains the same. The threshold for hearing, however, remember the threshold we're talking about, like when is the minimum we start hearing, oh my God, excuse me. I gotta, I'll be right back. Give me one quick second. Okay. Sorry about that. So the thresholds for hearing, meaning like when the minimum loudness that we hear is seen in this green line. And we see that it changes depending on the pitch that we're hearing. So if it's a low pitch, it starts around 80 decibels. And if it's a higher pitch, it kind of goes down. So what that's just meaning to say is that the squeakier the voice gets, the lower the loudness is that we require to hear it. So hopefully that makes sense. So then we have the ear itself. And the ear is something that you may have already seen in other classes. And so fortunately for this one and for the MCAT purposes, we don't have to worry too much about its structures. But I just want to point out kind of a couple of different things here. Sound enters the pinna, which is the opening of the ear, and it gets funneled in and it travels down the auditory canal. In the auditory canal, the sound gets amplified. That's important, right? Because we want the sound that gets caught in there to be amplified so we can really detect what the sound wave frequency is. And then the eardrum is a sort of membrane that's very taut and kind of like a drum, blocks what is known as the outer ear and the middle ear. When it vibrates, it's connected in the middle ear to a series of three tiny bones. I believe that the smallest bones that we have, that are called ossicles. They're called the malleus, the incus, and the stapes, and they're in that order. And their names come from a hammer, an anvil, and a stirrup, though that doesn't help me at all because I barely know what an anvil is. So I just like to think about them actually as malleus, incus, and stapes. And so those vibrations carry across in those bones, and then they hit something called the oval window, which divides, it's a membrane that divides the middle and the inner ear. And that one hits the structure called the cochlea. And so the cochlea is a deeper into in the inner ear. And the cochlea houses the part that's called the organ of Corti, which is the biggest fuss about this whole thing is like once we get down to this part. The second diagram I like because it shows how the vibration that comes from the stapes, which is that bone, hits the membrane, which is the oval window. And here, which is a fluid-filled chamber, begins to vibrate. And you can see in these dotted lines around the number 2 that they vibrate the organ of Corti. If we look a little bit closer to the organ of Corti, these are the bottom and low, the top and bottom openings are the chambers, and the organ of Corti is sandwiched in between them. In the right-hand diagram, the organ of Corti rests, is like this whole right-hand side diagram. And when you look down at the micro parts, there are 2 membranes in between it, the tectorial membrane and the basilar membrane. And the whole point of this whole process is to get mechanically from sound waves all the way here. Like that's really important. That's like, if I want you to take away from this crazy slide, one thing is that this whole process has been mechanical. There have been no chemical steps at this point. And so then they hit, the waves are the ones that pressurize the, oh, okay, cool. Somebody brought up a really good point. If you want to, I realize the PDF has overlapping images. So if you want to take individual snapshots of this one, and then that one's a cool one. I like that one. And then that one. The whole point of this is to arrive to the tectorial membrane, which through the vibrations excites the hair cells, which are these little funny blue things that are connected to the nerve, as you can see, exiting via the cochlear nerve. And those are also connected to the basilar membrane. So if I want you to get anything out of this whole slide is that the mechanical, not chemical, but mechanical transduction happens all the way up until it gets to the hair cells, and then it turns into a neural impulse. Okay. So when it comes to sensing hearing in the brain, we talked about how in visual senses, it arrives to the occipital lobe and then to the primary visual cortex. It has some stops along the way, but that's kind of where it ends up. For the auditory pathway, we're going to focus, and for the MCAT purposes, this is all you really need to know, is what happens as it gets to 2 places. So one is the thalamus, and that's the same place as the LGN in the visual pathway. But more importantly is the auditory cortex. And there's one in the auditory cortex that's located in the temporal lobe, which is called the primary auditory cortex. This diagram does a good example of showing what would happen if a retractor, it's kind of gross for me actually to see this, but what a retractor does, if you lift this part of the temporal membrane, and then you would be able to see an inner part of that. And that's where the primary cortex resides. The one important thing about this whole slide is this last point, this last bullet point, which is that neurons are arranged tonotopically. Highlight that term, tonotopically, as they are in the basilar membrane. I'm going to show you how they are in the basilar membrane in just a second. But tonotopically means is that the neurons are arranged in such a way where they would fire in the same way that, let me phrase that differently. Okay, neurons are spaced out according to which frequency they respond to best. Got that? Neurons are spaced out according to what frequencies they respond to best. As you can see from this diagram, you start from low frequency of 500 hertz and you increase to 600 hertz. This means that the things that will arrive to the primary, the impulses will arrive from the ear and the basilar membrane and innervate neurons in specific areas of the primary auditory cortex. That's truly all you need to know about that one. So now we talked about the visual senses. So in sight, we took like an hour to talk about visual sense and then another hour for perception. Now we just did visual auditory senses in 5 minutes, and truly that's all you need. And now we're going to do for the next 5 minutes or less perception. So perception is a subjective thing one more time. And there's one big theory you need to know about this. Actually, I think it's two big theories you need to know about this. One is place theory. And the place theory, I've given the definition in italics, and it's the perception of the pitch according to the vibration of different portions along the basilar membrane. So let me explain that instead of having the definition. What place theory is saying is that sound arrives through this whole auditory channel and arrives to the basilar membrane in the cochlea. This diagram shows the basilar membrane unraveled. And just like the primary auditory cortex that's arranged sonotopically, so is the basilar membrane arranged such that you have the really high frequencies first, and at the very end, the low frequencies. If you've ever played a piano, imagine the reverse, where the high keys are on your left-hand side and your low keys are on your right-hand side. That's exactly what you need to think about this. What this theory is saying is that sound must travel and only the right frequency will activate the right area. So imagine that a sound comes in of, let's say, 3,000 hertz, and it's traveling. And in order for this, everybody would ignore until, let's call this 1600, 1.6, not 3. So every one of these neurons here and here and here would ignore that until it arrived to here, and then boom, this one says, oh, you're the right frequency for me, and it gets activated. That's place theory. It means that the frequency that would arrive would only activate a specific spot or a specific place along the basilar membrane. Pretty straightforward. The assumption here that you have to keep in mind is that it means that the hair cells respond independently, meaning what I just said about like the other ones would ignore it. The other ones would ignore it up to 1600 hertz. Those function independently, meaning they wouldn't be affected. And then the other assumption is that each set of hair cells vibrate at specific frequencies. The other theory that I want you to keep in mind is frequency theory. There's just two of them. They're opposing, and you'll find out they happen to both be right. They should ring a bell because we've talked about trichromatic theory and opponent process theory in the other section. By the way, both of these theories are also in the 1800s. So the frequency theory is saying that the perception of the pitch corresponds to the rate of the vibration of the entire basilar membrane. So this is the easy way you can distinguish the two. This basically is saying that unlike the other diagram, this diagram shows that it's one basilar membrane. And it's saying that the frequency that comes in shakes the whole thing, the entire thing. And it shakes it at the same frequency that it comes in. And that message just gets relayed to the brain. Does that make sense? It's kind of like suddenly the whole thing is shaking. And depending on how fast it's shaking, the rate of shaking, that's what it's going to be sent to your brain and interpreted as a frequency of sound. So the assumption here is that the entire membrane vibrates. And the second assumption is that that the things that get transmitted is just how much it shakes. And then that's perceived as the frequency, as the pitch, excuse me. So here is where you can actually reconcile the two. So some things are right and some things aren't. Place theory is actually correct, except that the hair cells are not independent. What I mean by that is that, like I said in the first diagram, where that all of the hair cells were static until only one that was the right one for that frequency was activated. This is actually saying that no, like they aren't independent. They in fact vibrate together, like frequency theory said. So place theory was right in saying that yes, you activate a specific area of the basal membrane, a specific set of hair cells, but they actually all vibrate together. The point that gets activated is actually the peak. And I like this diagram because it shows you that it actually does this wave. You know, it's doing this little floppy wave where there's this peak where the arrow is leading. That's going to be the area that then gets sent to the brain as saying like, oh yeah, that's the place where the pitch is coming from. And so that's how we hear it. Not peak as an amplitude. Thank you for asking, Tiffany. No, I mean literally this like floppy, oh shit. This floppy peak right there. That's what I mean. So you see this thing is just doing the wave like that. So frequency theory is right, that the whole thing shakes. That it's not like only static until you get to this spot. But place theory is right in saying that it's this that's going to send the message over to the brain. Yeah, Brooke, for the purposes of the MCAT, we're not going to focus on exactly how many times it peaks. It's actually really complex, and the physics of it is really beautiful to go into. But just know that at some point, there will be a peak. There might be several, but there's one particular peak that will be the one that sends the message along to the brain that then places it in a pitch. Yeah. Okay. And then, yes, Tiffany, exactly. Yes. Exactly that. The whole thing shakes. So in that part, frequency theory is right, but only one area is the one that's going to send the signal to the primary auditory cortex, in which case place theory turned out to be correct. Exactly. Alrighty. Alrighty. So we finished it all. And this is the stuff that I propose that we talk about later, which is taste and smell, the sense of touch, and kinesthesia and proprioception. Believe it or not, they are not that crazily tested. And I can show that to you because here is an example of, not an example, this is the actual diagram shown of content category 6A. I bet you none of you are geeky enough to have seen this, or maybe you have. But if you go to the AAMC and you look for the PsychSoc content, you'll find that this is one of the content categories for PsychSoc. I think it's the entirety actually for PsychSoc. No, excuse me. This is the 6A means it's sensory processing. And we've talked about everything except for the stuff highlighted in blue. And those things that are highlighted in blue are things that we can actually do quite quickly. The other ones are the ones that are tested very heavily. And we've talked about everything, believe it or not, that's in this thing. And mostly thank you to your patients that we've talked about all these things because I found quite a bit over. So that is my last slide. And I am more than happy to use maybe the next 20 minutes to go over any questions. Thank you for, my goodness, you've survived that long. Apologies again, I gotta reformat that so that it goes a little faster. Are there any questions? Is anybody brain dead? Please say you're brain dead, otherwise you're not human. Okay, good, good. Good. I could definitely go over those kinds of things, but let me ask you really quick. Do you have a clear sense of bottom up and top down process? Good. Do you have a clear sense of the difference between trichromatic theory and opponent process theory? In its basics. Watermelon. Oh, we need to talk about the watermelon. I need to get back to you about that. No. Okay. Place theory and frequency theory. Gestalt to stop down. That's right. Alrighty. And the last thing that I want you to never ever forget is the optic chiasm. Do you understand why we have ipsilateral and contralateral motion? And why it's helpful even if we only have vision through one eye? So you can still, yeah, let me refine that, Michaela. So you can still see both sides of the visual field. Exactly. Exactly. Okay. All right. So for homework, my recommendation is that you look at, yeah, Jonathan, I can go through it. Wait, okay, let me get organized before it gets crazy. Okay, because I realize some of you might not be here anymore. So let me figure out office hours first. I saw Patricio has office hours Tuesday, 11 to 2, and Koi has Monday, 4 to 5, and some odd Wednesdays, 4 to 5. I was going to propose Wednesdays, 11 to 1. How does that sound? Yeah. Mm, 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 mm. Let's see. Yeah, weekends. Saturday or Sunday mornings. I wouldn't want to do it after the classes because we all tend to run late, so I don't want to conflict with that. Um, yeah, you have lectures Saturday and Sundays. I think the best way to do about this would be maybe a poll because I'm beginning to see this might. Yeah, maybe I could do a doodle. I'm gonna do a doodle. I'm gonna do that. I'm gonna put all of my available times, and we're gonna do a doodle. For those of you who didn't get my email who are still here, for you surviving heroes this morning, that means that the list that we were given as instructors is not accurate. So please message Todd or Josh, whose email you probably have, and let them know. So if you're one of those people who didn't get my slides this morning, or if it didn't end up in spam, then you need to update that one, because it's not just me, it's other people who are probably sending you stuff. Okay, I'm going to do a doodle. And then my recommendation for you is to do passage 1. We can do it together, if you allow me to have a bike break. But if not, at home, I recommend you do passage 1 and passage 4 for this. Did you get that? Passage 1, passage 4. Let me write that down. Okay, I got that, Jonathan. No, yeah, good question. No, I'm talking about section 1, human senses. You'll notice I didn't talk about anything from chapter 1, otherwise known as section 1. That is like really just a refresher on the neurobiology, and that's like everything you already got from the lecture yesterday. It's exactly what you got. It has endocrine stuff, and yeah, I wouldn't recommend that, to be honest, unless you have like extra time, which none of you probably do. Focus on section 2, or chapter 2, however you want to call it, and passages 1 and passages 4, and all of the discrete questions. There are not very many of them, so it would be good practice. The next thing I would do after that is actually not finish all of those, but instead go to Khan Academy and then go to the senses and go to visual and go to hearing and practice everything you just learned here. There's nothing. I went over by 40 minutes, but there's nothing I didn't cover that you would need to complete all those things. One detail I didn't talk about, one single one, which was motion parallax. That's the only one. But we can talk about that later. Okay. So I was going to originally propose office hours from 1 hour after lecture. We have 14 more minutes. What do you guys want to do? Where on Khan Academy do we see the practice? Yeah, if you go to actually, let me see if I can send you all this handout. This is a handout that's actually in the portal, I believe. Let me see if I can find it. This handout in the portal has Khan Academy links. Okay. Okay, hopefully you got a PDF in the chat box. It's a handout that is actually I'm just scrolling through it really quick to see if what I said is true. But if you go to the very bottom of it, oh, it must be a different one. Shoot. Oh no. Okay, if you go to page 3 of that handout, it suggests passages from Khan Academy, and they call it phase 1 passages and phase 2 passages that you take from Khan Academy, and there's the link right there. Hopefully somebody's able to open it and see that on page 3, there's indications what to do for phase 1 and phase 3. Tiffany, yes, I can most certainly explain closure and subjective contour. Closure is a Gestalt law. So that's one thing you need to remember, and that and subjective contour is not a Gestalt principle. However, it's the same mechanism that's happening in both of those. The only thing I would say that's different about subjective contour, Tiffany, is that if you remember, and if you don't, I can open up the slides back. But if you remember for closure for the Gestalt principle, there was a picture of what looked like a fox. So for the contour one, for the closure, the closing of those lines rendered the fox. Subjective contour is a little different because that one focuses more on sort of the negative spaces. If you can remember the example, it was Pac-Man's going around different shapes. So they're slightly different concepts, though the mechanisms that are happening in our brain are similar ones. Yes, exactly. Closing the dots and following the lines. And subjective contour is not about following any lines. It's about what surrounds the contour. Yeah, exactly. For both of those, it's subjective. They both fall under the perception part, not the sensation. Just remember that one is the Gestalt principle and the other one is not. The other one was actually the subjective one, subjective contours I brought up because it was opposition to feature analysis, which was saying that the way that we perceive is by looking at features and then building a whole. And subjective contours was evidence that's not the case because we could see shapes even though there were none. which was an example of top-down processing. Any other questions I can answer in the next 9 minutes? Yeah, I'd love, thank you for bringing up the Weber. So this is really awful. How do I show this? Sorry, it'll take me a little second and or it'll be ugly to see with me using my cursor. Weber's law. So if we're told in a problem that k is 0.037, can you tell me in the way that I worked out, and this might not necessarily work for you, maybe you're really good with decimals, but me and most normal humans aren't. How do you turn that into a nice looking fraction? Right, right. So the way that I would do it is calling it 37 over 100. So Noah, I like using this method because it's something I can actually hold on to. If you're really good with the concept, you can just use the constant, but I like to do this fraction because this is true. This equivalence that I did is true. So with equivalence, if I double it, this is gonna also be true. 200. What is 37 times 2? 60 plus 14, 80, 70, 74? I'm so sorry, folks. I don't know what just happened. It looked like I got kicked out. I don't know if you saw what I saw. Oh, sorry, folks. I'll finish this example on the chat box, which is saying that 0.037 equals 37 over 100, which equals 74 over 200. No, if you're still here, does that make sense? How those are equivalent? So what I like, right, yeah, Sophie, yeah, you're getting at it. So what I like about these examples is that it's something I can easily hold on to, and I can always reference this example of using weights. So, God, I can barely lift anything, but I certainly can't lift 100. But let's say I can lift 100 pounds. What this constant tells me is that if my initial stimulant, it doesn't have to be 100, it could be 200. But what it's saying is that if it's 100, then the next noticeable difference that's going to be like, oh, I can notice that it got heavier, is going to be when it's 37 pounds heavier. So 137 pounds. Let's say I start with 200 pounds. The next weight that I'm going to notice as being as heavier is not going to be by adding 37 pounds. It's actually have to add 74 pounds. Does that make a little bit more sense? Yeah. So my recommendation with Weber's law is with the constant, always put it out into basic numbers. And usually when you do something basic, you're doing it the right way for the MCAT. If you're going complicated, you're probably like doing not what the MCAT wants you to do. So I always turn the constant into a decimal, and I do it always dividing it by 1, 10, 100, because it's always easier. And from there, you can kind of extrapolate. Any other questions? Blue watermelon. Michaela, that one I have to research. I promise I will research that one and I also wrote down I have to get you good examples from Tonic and Faceit. But blue watermelon was basically uh, what I wrote down, and I have to confirm and better explain why, is that it supports the trichromatic theory of color, which basically is saying that we have three colors that we see, three receptors that see in three different colors. Um, and so yeah, so that I'll get back to you, Michaela, about specifically what the phenomena is and how it's a support for it. But I want you to know now, though, that that's not definitely something you have to stress about for the MCAT. What you do have to stress about is that the trichromatic theory of color, two things about it, that it says that you have those three kinds of receptors that are sensitive to those frequencies of light, and that then we figured out later on that this actually was the case. Because remember how I showed those two theories and then showed like, oh, modern research shows that they were elements were right. And it does show that that there are that there are cones in the retina that are sensitive to those frequencies, most sensitive to those frequencies of light. Does that make sense? Okay, cool. Yes. No. Yeah. More likely than not. Yeah. And I think passage one has a good. It's passage one or passage four that I recommended to you. Has a good question on just noticeable differences with a Weber's law in there. Yeah, I mean, Weber's law is one of those things that they like to throw in there because it's particularly scary if you don't have the basics down for it. But once you do, the just noticeable difference is actually is very easy to figure out with the Weber's law. Yeah, it's one of those nice validating ones where like it's really scary, but once you have the basic formula down, you kind of enjoy seeing them because you're like you can solve it. Online service you took. Um, yeah, so for Makila, I would suggest make the number one suggestion I would do for the course is make a study buddy or buddies. Not too many of them because then it stops losing its effectiveness, but one or two. Pick them, pick the ones who have similar work schedules as you, and then and such that you can create a calendar of sticking to phase 1, 2, and 3 uh, progression. So do that. Yeah, it was super important for me to have specific people that like I could keep accountable to, and then we would create like little. We would actually put in our schedules like, okay, we're gonna meet like all of us with our little Zooms, camera ons and muted, and we're gonna do phase ones, regardless of whether we've done the reading or not, but just so that we can keep up with the questions. No, that's a really good question. So red green colorblind, what you see is the after image of the blue watermelon. So that would mean that red, blue, blue and red. Oh my gosh, I think you would see white. Uh, I think you would see white as the after image. That's a good question. I wonder. That's I think that would. I think that's Gosh, you and the. I should have never brought up this watermelon. Let me. I'll look into that one. Uh, okay. Um, I'll look into that one and report back to you all. Um, okay. Um, Alrighty, folks. We've hit. Thank you, Jonathan, for. And now it's like, now I hate that one. No, thank you so much for joining in, especially for all of y'all that stuck with me to the bitter end. It was my bad that I didn't uh, finish on time. But what I really wanted to do you justice with these psych lessons is that my experience of taking the psych lessons as well as like psych materials is that there's just a lot of psych material out there and a lot of way of presenting it, but very few of them have flow and logic. And so I really wanted as best to kind of get the thing that I wish I would have gotten, which was like really understanding the progression of like what is all these terms and embedded in kind of real examples. So hopefully I did an okay job of showing you that. And hopefully it justifies the fact that uh, and that hopefully it justifies the fact that we spent a little bit more time. So I'm going to send a doodle poll, and hopefully we can find some times that work with the majority of the people so that we can cover some of the topics that we've missed, as well as just have regular office hours where we can talk about psych stuff or any other subjects that you want. Maybe just don't hit me with torque and maybe cars. Yeah, some of them I'll just like flat out say like, no, we're not talking about that. But yeah, we can talk about almost any subject that you want. And then and yeah, my other thought process was that if we have oh, Sophie, you're the only person in the world. God bless you. Um, if there's such a disparity in terms of people's availability for office hours, maybe I'll consider potentially recording one of those sections so that people can do it in their own time asynchronously. My only hesitation is that there's that it's Berkeley Review intellectual property, so I think there might be some hiccups about videos floating around there. So if I can figure out a way for something to be like you see once and it disappears, maybe I can do something like that. But anyways, I'll let you know. Anyways, thank you so much for your time, everybody. I'll let you go. Please go have some breakfast if you haven't yet, or some lunch. Remember to look at the stars tonight and practice understanding why you can't focus on the phobia. Exactly. Exactly. Okay, everybody, have a great rest of the day, and we'll see you soon in 2 weeks. Bye-bye.